What if everything we've ever seen, touched, or known, every star, every galaxy, even time itself, is just the tiniest glimpse of reality's true depth? Imagine standing at the edge of an infinite ocean, but all you can perceive is the shimmering surface, completely unaware of the vast, hidden currents surging beneath. For centuries, humanity has gazed at the night sky in awe, charting the movements of planets and stars, believing we were mapping the cosmos. But what if the real architects of the universe have been hiding in plain sight all along, forces so subtle, so powerful, they've escaped our detection while shaping existence itself? Welcome to a journey beyond the visible, into the heart of the unseen. We're about to uncover the hidden hands that pull the strings of reality from dark energy, mysteriously stretching the fabric of space faster and faster, to quantum fluctuations that conjure particles from nothingness, defying everything we thought we knew about emptiness and form. These are not just abstract ideas tucked away in physics textbooks. They are active, breathtaking influences that guide the birth of galaxies, the flow of time, and perhaps even the existence of other worlds, parallel universes existing just beyond the veil of our perception. This video is your invitation to explore 30 of these invisible powers, each more astonishing than the last. Together, we'll venture into realms where matter is outnumbered by shadowy counterparts, where gravity is not always what it seems, and where the universe whispers its deepest secrets through forces we are only beginning to understand. You'll come away not just with knowledge, but with a renewed sense of wonder, a feeling that the cosmos is far grander, stranger, and more alive than you ever imagined. So settle in, open your mind, and prepare to see the universe in a whole new light. The hidden forces are waiting. Our journey into the unseen begins with perhaps the most profound and baffling force of all, dark energy. Think of the universe not as a collection of stars and galaxies, but as a vast, rising loaf of raisin bread. Each raisin is a galaxy, and as the dough expands, every raisin moves away from every other one. Now imagine that loaf of bread began to rise faster and faster, accelerating without any apparent cause. This is precisely what astronomers observed in the late 1990s. The universe's expansion isn't slowing down due to gravity, as everyone expected, but is instead speeding up. Something is actively pushing space itself apart, and we've named this mysterious something dark energy. What makes this force so enigmatic is its sheer dominance and its elusiveness. Dark energy is not a small player. It constitutes about 68% of the entire energy density of the cosmos. That means the force driving the acceleration of the universe makes up more than 2/3 of all the stuff in existence, yet it is completely undetectable by any telescope or instrument we have. It doesn't emit light, absorb light, or interact with matter in any way we can directly observe. We only know it's there by witnessing its breathtaking effect on the largest canvas possible, the entire universe. This leads us to one of the most unsettling fine-tuning problems in all of science, the cosmological constant problem. When we try to calculate the theoretical strength of dark energy based on our understanding of quantum physics, the number we get is absurdly, unimaginably large, about 120 orders of magnitude too strong. That's a 1 followed by 120 zeros. A universe with that much repulsive force would have torn itself apart instantly after the Big Bang, preventing stars, planets, or life from ever forming. Yet, the actual measured value of dark energy is extraordinarily small and perfectly balanced, allowing for the cosmos we see today. This discrepancy is so vast it's like predicting a tsunami, but instead finding a single, gentle ripple in a pond. It suggests one of two incredible possibilities. Either we are the beneficiaries of an almost impossible cosmic coincidence, or there is something fundamentally and deeply wrong with our understanding of physics on its most basic level. But if dark energy is the enigmatic force pushing the universe apart, what is it that holds everything together? This brings us to the cosmic glue, the invisible scaffolding of the cosmos, dark matter. While dark energy works on the grandest scales, accelerating the expansion of the universe, dark matter operates on the scale of galaxies and clusters, providing the gravitational backbone that allows them to form and endure. We cannot see it, touch it, or interact with it in any conventional way, yet its gravitational signature is unmistakable and overwhelming. It is the universe's most influential ghost. Our first compelling clue for this unseen substance came from the careful observation of how galaxies spin. Imagine a merry-go-round. Objects placed near the edge have to move much faster to avoid flying off than those closer to the center. Astronomers expected to see the same behavior in galaxies. Stars on the outer edges should orbit more slowly than those near the bright, dense core. Yet when they measured the orbital speeds of stars in spiral galaxies, they found something astonishing. The stars on the outskirts were moving just as fast as those near the center. The only plausible explanation was that each galaxy was embedded within a massive, invisible sphere of matter, a halo exerting a tremendous gravitational pull, preventing those high-speed outer stars from being flung out into the void. This matter, which does not emit or absorb light, was named dark matter. Further, and perhaps even more dramatic, evidence comes from a phenomenon predicted by Einstein's theory of general relativity, gravitational lensing. The presence of mass warps the very fabric of space-time, bending the path of light that travels through it. When astronomers look at massive galaxy clusters, they sometimes see distant galaxies behind them stretched and distorted into faint, shimmering arcs of light. This is the cluster's gravity acting like a giant, cosmic magnifying glass. The incredible part is that the amount of bending observed is far too great to be caused by the visible stars and gas alone. There must be an enormous amount of invisible mass within the cluster, its gravity warping the light from behind it. We are literally seeing the shadow of dark matter. This mysterious substance is not a minor component of the universe. It is a fundamental part of its structure. Dark matter makes up about 27% of the cosmos, outmatching all the atoms that make up stars, planets, and every one of us by a factor of about 5 to 1. In the early universe, it acted as a gravitational seed. While normal matter was pushed and buffeted by the intense radiation of the Big Bang, dark matter, unaffected by light, could quietly clump together under its own gravity. These initial clumps created the gravitational wells that later drew in the normal matter, forming the first galaxies and eventually the vast cosmic web, the intricate, filamentary structure of galaxies we observe spanning the emptiness of space. A pressing question, of course, is what dark matter actually is. For decades, the leading candidates have been WIMP, or weakly interacting massive particles. These are theoretical particles that are heavy, move relatively slowly, and, as their name implies, interact with normal matter only through gravity and the weak nuclear force, making them extraordinarily difficult to detect. Scientists have built incredibly sensitive experiments deep underground, in abandoned mines and tunnels, to shield them from cosmic rays in the hope that a WIMP might, on very rare occasion, bump into an atomic nucleus and create a detectable signal. So far, these detectors have remained silent. Another compelling candidate is the action, a hypothetical particle that is billions of times lighter than an electron but potentially incredibly abundant. Actions were originally proposed to solve a different puzzle in particle physics, but they also possess the right properties to be dark matter. Unlike WIMP, actions would be so light and feebly interacting that they would behave less like discrete particles and more like a pervasive, invisible energy field oscillating throughout the universe. Innovative experiments using powerful magnetic fields are now searching for the faint whisper of an action converting into a photon. The hunt continues, and each null result deepens the mystery. We know dark matter is there. We can map its distribution across the sky by watching how it bends light. We know it shaped the universe, but its true nature remains one of the most profound puzzles in modern science, a silent reminder that most of the cosmos is made of something entirely unknown to us. If dark matter and dark energy represent the invisible scaffolding and engine of the cosmos, then the very stage upon which they act, the vacuum of space itself, holds a secret just as astonishing. We are taught that a vacuum is the very definition of nothingness, a complete and utter void. But what if I told you that the emptiest space in the universe is in fact a seething, bubbling cauldron of activity? This isn't just a philosophical idea, it's a fundamental prediction of quantum mechanics, and we have the experiments to prove it. This brings us to our third unseen force, quantum vacuum fluctuations. At the heart of this concept is Werner Heisenberg's famous uncertainty principle, which tells us that on the tiniest scales, the universe is inherently fuzzy. We cannot know both the exact energy of a system and the exact time that energy exists. This leads to a breathtaking consequence: empty space can never truly be at zero energy. Instead, for fleeting moments, pairs of particles and their opposite antiparticles, so-called virtual particles, can spontaneously erupt into existence, borrowing energy from the void before almost instantly annihilating each other and paying that energy back. This isn't a theory about what might be happening, it is what is happening everywhere all the time. The vacuum of space is a quantum foam, a perpetual dance of creation and destruction happening over timescales so short we can never directly see it. But if we can't see these particles, how do we know they're real? We know because they leave a fingerprint, a measurable force. In the 1940s, a Dutch physicist named Hendrik Casimir predicted a brilliant experiment. He imagined placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum. Outside the plates, every wavelength of these virtual particles can exist. But in the narrow gap between the plates, only certain specific wavelengths can fit. This creates an imbalance in the quantum pressure. There are simply more virtual particles and fluctuating fields pushing on the plates from the outside than from the inside. The result: the plates are pushed together by the nothingness itself. This Casimir effect was experimentally confirmed and is now a standard demonstration of the power of quantum fluctuations. The void is not passive, it exerts a real physical force. This incredible activity of the vacuum may have played the most important role of all, sparking the entire universe into being. The leading theory for our cosmos's first moments is called inflation. It proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion, smoothing it out and planting the seeds for all future structure. And what could have powered this incredible growth? Many physicists believe it was a peculiar state of the quantum vacuum itself. A field known as the inflaton might have become trapped in a high-energy state, and its subsequent decay, its release of vacuum energy, would have acted like a cosmic engine, driving that monstrous inflation. In this view, the entire observable universe could be the product of a single, monumental vacuum fluctuation. This idea also brings us back full circle to one of our greatest mysteries: dark energy. When physicists try to calculate the energy density of this quantum vacuum, the sum of all that particle popping activity, they aim to explain the force we now call dark energy. But as we discussed, the calculation goes catastrophically wrong. The theoretical value is 1 followed by 120 zeros too large. This isn't just a minor error, it is the single greatest discrepancy between theory and observation in all of science. It means we are profoundly missing something. Either our understanding of the quantum vacuum is deeply incomplete, or dark energy is something else entirely, and the vacuum energy is being cancelled out or hidden by a mechanism we have yet to discover. The hum of empty space, it seems, still holds the key to the universe's ultimate fate. This invisible engine of creation, cosmic inflation, addresses some of the most perplexing questions about our universe. Why does the cosmos appear so incredibly uniform in all directions? Why is the geometry of space so flat, following the rules of Euclidean geometry we learned in school, rather than being dramatically curved? And perhaps most puzzling of all, why did we never detect any of the magnetic monsters known as magnetic monopoles that most grand unified theories predict should be everywhere? The theory of inflation elegantly solves all three. By stretching a tiny, subatomic patch of space to become larger than the entire observable universe in a fraction of a second, inflation took whatever was inside that patch and smoothed it out to incredible uniformity, ironing out any wrinkles or curvature and diluting any exotic relics like monopoles to undetectable levels. But this process of smoothing was not perfect, and that imperfection is the reason we exist. Due to the quantum foam nature of reality we just discussed, the inflationary field itself was subject to tiny, random fluctuations. As space expanded at a mind-boggling rate, these infinitesimal quantum jitters were stretched from the subatomic to the astronomical, frozen into the fabric of the universe as faint ripples in the density of matter and energy. These ripples became the gravitational seeds for everything that followed. Slightly denser regions had a bit more gravitational pull, slowly drawing in more dark matter and gas over hundreds of millions of years, eventually collapsing to form the first stars, galaxies, and the vast cosmic web. The entire large-scale structure of our universe originated from these quantum whispers amplified to cosmic proportions. We can actually see the afterglow of this event imprinted on the sky. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons, forming the first atoms and allowing light to travel freely for the first time. That light, now stretched by the expansion of the universe into microwaves, fills the entire sky. It's the cosmic microwave background. Satellites like the Planck mission have mapped this background radiation with exquisite precision, and it reveals a pattern of tiny temperature variations, hotter and colder spots that correspond directly to those primordial density ripples. This map is essentially a baby picture of the universe, and its statistical properties match the predictions of inflationary theory so precisely that it is considered one of the strongest pieces of evidence we have. The driving force behind this explosive expansion is thought to be a hypothetical field called the inflaton. Imagine a ball resting at the top of a very flat, very high hill. This high energy state of the inflaton field is what powered the exponential expansion. As the ball eventually began to roll down the hill, inflation ended, and the energy stored in the field was released in a torrent, reheating the universe and filling it with the hot plasma of particles that would eventually form all the atoms around us. But what set this field in motion, and what is its true nature? This remains one of the most active areas of research in cosmology, connecting the physics of the very largest scales to the very smallest. Perhaps the most staggering implication of inflation is the possibility of a multiverse. The theory suggests that once inflation starts, it may be eternal. While it ends in our patch of the universe, creating our observable cosmos, quantum fluctuations could cause it to continue in others, spawning an infinite number of separate bubble universes, each with potentially different physical constants and laws. In this breathtaking view, our entire universe is just one bubble in a vast, ever-expanding cosmic foam, a single outcome in a landscape of infinite possibilities. Now, if these cosmic forces like inflation and dark energy shape the universe on the grandest scales, there exists another phenomenon operating on the smallest scales that is equally profound and perhaps even more baffling. It's a connection so intimate and instantaneous that it seems to defy the very nature of space and time, a concept that Einstein himself famously dismissed as spooky action at a distance. This is the strange and beautiful world of quantum entanglement. At its heart, entanglement is a connection forged at the birth of particles. Imagine two electrons being created together in a single event. According to the rules of quantum mechanics, their properties like their spin, a kind of intrinsic angular momentum, are not defined individually but are intertwined. They exist in a shared, fuzzy quantum state. It's not that one particle has spin up and the other has spin down. It's that both possibilities are superimposed, a delicate mixture of maybes until the moment one is measured. And here's where reality gets weird. The instant you measure one electron and find its spin to be, say, up, the other particle's spin instantly becomes down, no matter how far apart they have traveled. This change is immediate, seemingly bypassing the universal speed limit of light. One particle doesn't send a signal to the other. The information appears to be shared outside of the channels of space and time as we understand them. This challenges two fundamental pillars of classical physics: locality, the idea that objects are only influenced by their immediate surroundings, and realism, the idea that objects have definite properties even when we're not looking at them. For decades, this was a philosophical debate, a thought experiment highlighting the apparent absurdity of quantum theory. That changed with the work of physicist John Bell in the 1960s. Bell devised an ingenious mathematical theorem that could, in principle, test whether this spooky action was real or if some deeper, hidden variables were at play, preserving a more classical view of reality. The experiments, first conducted in earnest in the 1980s by Alain Aspect and his team, were decisive. They repeatedly showed that entangled particles are correlated in ways that no local, hidden variable theory could ever explain. The universe at its core is non-local, entanglement is real. This wasn't just a laboratory curiosity confined to a tabletop. Subsequent experiments have pushed the boundaries of this quantum link to astonishing distances. Researchers have successfully entangled particles and then separated them by over 1,000 kilometers, sending one photon to a satellite in orbit and keeping its partner on Earth. Even across that vast, empty gulf, the instantaneous connection held. The act of measuring the particle in space irrevocably set the state of its partner on the ground. This isn't some faint, weakening signal. It's a fundamental property of how the universe is wired, a thread of correlation that weaves through the cosmos completely independent of distance. The practical implications of this are revolutionary, giving rise to the fields of quantum computing and quantum communication. In a quantum computer, entangled quantum bits or qubits can be linked together to perform calculations in parallel, exploring a vast number of possibilities simultaneously. A problem that would take a classical supercomputer thousands of years to solve could be cracked by a sufficiently powerful quantum machine in a matter of hours. Quantum communication, or more specifically, quantum key distribution, uses entanglement to create theoretically unbreakable encryption. Any attempt to eavesdrop on a message secured by entangled photons would immediately disturb their delicate quantum state, alerting the sender and receiver to the intrusion. This is the beginning of a truly secure internet, a network protected by the fundamental laws of physics. But perhaps the most mind-bending implication of entanglement reaches back to the nature of reality itself and ties into concepts like the holographic principle. This principle suggests that all the information contained within a volume of space, a room, a planet, even our entire three-dimensional universe, might actually be encoded on its two-dimensional boundary like a cosmic projector screen. And how is that information shared and connected across the entire volume? The primary candidate is a vast, complex web of quantum entanglement. In this view, the seemingly empty space between stars and galaxies isn't truly empty. It's stitched together by countless entangled particles, creating the very fabric of spacetime from a network of quantum connections. Entanglement might not just be a feature of the universe. It could be the glue that holds reality together, the invisible force that allows a seamless, coherent cosmos to emerge from a foundation of quantum uncertainty. While quantum entanglement weaves an invisible web of connection across the cosmos, Another omnipresent field is responsible for giving substance and structure to the universe itself. This is the Higgs field, an energy field that permeates every inch of the cosmos, from the deepest voids of intergalactic space to the air in your lungs. Its sole purpose is to interact with fundamental particles, bestowing upon them the property we know as mass. Without it, the universe would be a radically different and far less interesting place. To understand how this works, imagine the Higgs field as a vast, invisible ocean of cosmic molasses that fills the entire universe. Particles moving through this field interact with it to varying degrees. Those that interact very strongly, like the top quark, are slowed down tremendously, acquiring a great deal of mass and becoming heavy. Particles that interact only weakly, like electrons, glide through with much less resistance, ending up with very little mass. And particles that don't interact with the field at all, like photons of light, zip through completely unimpeded at the speed of light, remaining entirely massless. This process, known as the Higgs mechanism, is the reason why the fundamental building blocks of matter have the weights they do. It's not an intrinsic property. It's granted by a universal field they are constantly moving through. For decades, this was a beautiful but unproven theory. The smoking gun, the definitive proof that this field was real, would be to detect its smallest possible excitation, a ripple in the field known as the Higgs boson. Finding this particle would confirm that the field itself exists. This quest culminated in one of the greatest scientific endeavors in human history at the Large Hadron Collider at CERN. Inside a 17-mile circular tunnel beneath the French-Swiss border, protons are accelerated to nearly the speed of light and smashed together with incredible energy, recreating the conditions a fraction of a second after the Big Bang. From the debris of these collisions, physicists sifted through unimaginable amounts of data, and in July 2012, they announced the discovery of a new particle with the exact properties predicted for the Higgs boson. It was a monumental triumph, the final piece of the standard model of particle physics falling perfectly into place. Yet, this discovery didn't close the book on the Higgs field. It opened a new and even more profound chapter of mysteries. The mass of the Higgs boson itself, at about 125 billion electron volts, is puzzlingly light. According to our best calculations of quantum mechanics, the Higgs mass should be susceptible to enormous corrections from its interactions with every other particle in the universe. These virtual particles popping in and out of existence in the quantum vacuum should drive the Higgs mass up to the highest energy scales possible, perhaps as high as the Planck scale, which is a quadrillion times heavier than what we observe. This is known as the hierarchy problem. The fact that the mass is so finely tuned to a low value suggests something is protecting it, acting as a cosmic counterbalance to keep it light. This is where the door to new physics swings wide open. The most popular theoretical solution is a concept called supersymmetry. This elegant theory proposes that every known particle has a massive, yet-to-be-discovered, superpartner particle. The beautiful mathematical symmetry of this idea would cause the quantum contributions from these superpartners to perfectly cancel out the enormous corrections from their standard partners, naturally stabilizing the Higgs mass at its observed low value. Supersymmetry would not only solve this puzzle but also provide a compelling candidate for dark matter and offer a potential path toward a grand unified theory of all forces. However, despite extensive searches at the Large Hadron Collider and elsewhere, no evidence for these superpartners has been found, leaving physicists to wonder if nature has a different trick up its sleeve. Other fascinating possibilities exist, such as the Higgs field being not elementary but a composite particle made of even more fundamental constituents, or our universe being part of a multiverse where the Higgs mass is a random variable, and we simply reside in a rare universe where it has a value suitable for life. The discovery of the Higgs boson was not an end point, it was a beacon illuminating a new path forward into the unknown. The precise properties of the Higgs, how it interacts, how it decays, are now the subject of intense scrutiny, as any tiny deviation from the predictions of the standard model could be the first clue leading us to the next deeper layer of reality. Just as the Higgs field gives particles their substance, another prediction of Einstein's theory of relativity paints the cosmos as a dynamic, flexible fabric that can ripple and wave. These are gravitational waves, and their detection opened an entirely new window on the universe, allowing us to literally hear the cosmos for the first time. To understand these waves, we need to revisit Einstein's revolutionary view of gravity. He proposed that gravity is not a mysterious force pulling objects together, but rather the result of mass and energy warping the very fabric of space and time, which we call spacetime. Picture a taut rubber sheet. Place a heavy bowling ball in the center, and it creates a deep depression. Now roll a marble near it. The marble will spiral inward, not because of a force, but because it's following the curved path of the sheet. This is how planets orbit stars, but what happens if you rapidly wobble that bowling ball back and forth? The rubber sheet wouldn't just bend statically, it would send out ripples across its entire surface. In the cosmos, the most violent events, like two ultra-dense black holes spinning around each other at nearly the speed of light, act as that wobbling bowling ball, sending out ripples in the fabric of spacetime itself. These ripples are gravitational waves. For a century, these waves remained a theoretical prediction. The challenge was their incredible subtlety. By the time these ripples from a cataclysmic event millions of light years away reach Earth, they are astonishingly faint, distorting the fabric of space by a distance thousands of times smaller than the width of a proton. Detecting this was arguably one of the most ambitious experimental quests ever undertaken. The tool that finally achieved it is a masterpiece of precision engineering, the Laser Interferometer Gravitational Wave Observatory, or LIGO. A LIGO observatory consists of two immense multi-kilometer long vacuum tubes arranged in an L shape. A powerful laser beam is split and sent racing down each identical arm, reflected by mirrors and then recombined. In calm spacetime, the light waves return perfectly aligned and cancel each other out. But when a gravitational wave passes through Earth, it does a remarkable thing. It briefly stretches space in one direction while simultaneously squeezing it in the perpendicular direction. This microscopic distortion changes the length of one arm relative to the other by an almost imperceptible amount. The laser beams, now traveling slightly different distances, fall out of sync. When they recombine, they no longer cancel out perfectly. Instead, they create a tiny, measurable flicker of light, a clear signal that spacetime itself has been disturbed. After decades of development to achieve almost unbelievable sensitivity, that first flicker was detected on September 14, 2015. The signal, named GW150914 after the date of its discovery, was the sound of two black holes, one about 36 times the mass of the Sun and the other 29, colliding over 1 billion light-years away. In a fraction of a second, they spiraled together and merged, converting an amount of mass equivalent to 3 suns directly into energy in the form of gravitational waves, shaking the very foundations of spacetime. The detection was not just a confirmation of Einstein's genius, it was the birth of an entirely new field of astronomy. Since that first historic chirp, LIGO and its international partners like Virgo in Italy and Kagra in Japan have detected dozens of these cosmic events. Each one tells a unique story. We've heard the mergers of more black hole pairs, building a census of these dark objects that are invisible to traditional telescopes. Perhaps even more exciting was the detection in August 2017 of two neutron stars colliding. This event was a multi-messenger astronomy bonanza. While the gravitational wave observatories felt the spacetime ripples, telescopes across the globe and in space were able to see the corresponding flash of light and gamma rays and detect the creation of heavy elements like gold and platinum forged in the incredible violence of the collision. For the first time, we could not only hear the event but also see it, unlocking secrets of nuclear physics and cosmic alchemy. This new sense of hearing is revolutionizing our understanding of the universe. Gravitational waves are allowing us to probe the most extreme environments imaginable, testing gravity itself in regimes where it is incredibly strong and dynamic. They provide a direct way to measure the properties of black holes and neutron stars, confirming their existence and revealing how they form and evolve. And as our detectors become even more sensitive, we will listen for the faint rumble from the very beginning of time, potentially from the primordial gravitational waves generated by inflation itself, giving us a direct glimpse into the birth of the cosmos. While the dance of gravitational waves reveals the dynamic warping of spacetime, another invisible force weaves through the cosmos with a subtler yet equally profound influence. We often think of magnetism as a local phenomenon, the pull of a compass needle, the force that holds a child's drawing to a refrigerator. But magnetic fields are a universal constant, a hidden architecture stretching from the hearts of planets to the vast, empty voids between galaxy clusters. They are the cosmic currents that guide the flow of creation itself. These fields are not mere bystanders, they are active players in the evolution of the universe. Within the swirling, collapsing clouds of gas that birth new stars, magnetic fields provide a critical support structure, a form of cosmic pressure that fights against the relentless pull of gravity. This magnetic resistance slows the process of star formation, preventing the entire cloud from collapsing at once and ultimately determining the final size and distribution of the newborn stars. Without this invisible scaffolding, galaxies might blaze with a frenzy of short-lived massive stars, drastically altering the cosmic landscape and potentially making stable, life-friendly solar systems like ours far less common. On a grander scale, magnetic fields thread through the entire interstellar medium, the thin soup of gas and dust between stars. They channel the flow of hot plasma, influence the structure of colossal gas clouds, and even accelerate particles to nearly the speed of light, creating the enigmatic cosmic rays that constantly bombard our planet. The origin of these immense fields, however, is one of cosmology's great unsolved puzzles. How did a universe that began, as far as we know, without any large-scale magnetic structure come to be so thoroughly magnetized? Scientists are actively pursuing two leading theories. The first is a primordial origin. This idea suggests that magnetic fields were generated in the extreme conditions of the very early universe, perhaps during the phase transitions of the hot Big Bang or the violent period of inflation itself. These faint seed fields, weaker than those in a modern MRI machine, would then have been stretched and woven throughout the cosmos as it expanded, providing the initial threads for later amplification. The second theory relies on a remarkable cosmic process known as the battery effect. Imagine a vast, spinning galaxy made of ionized gas, a plasma where electrons are stripped from their atoms. In such a system, the centrifugal force from the rotation pushes positive ions and negative electrons outward slightly differently due to their vastly different masses. This tiny separation of charge creates a weak electric current, and as any physics student knows, an electric current generates a magnetic field. This is the Biermann battery mechanism in action, a natural dynamo that could have jump-started magnetic fields in the first protogalaxies. Once even a minuscule seed field exists, a second process takes over, the dynamo effect. As the galaxy rotates, its turbulent, conductive plasma can stretch, twist, and fold these magnetic field lines, transferring the immense kinetic energy of the spinning galaxy into magnetic energy, amplifying the field over millions of years into the powerful forces we observe today. Wherever these fields exist, they leave their mark on the cosmos. They shape the spectacular jets of material screaming away from supermassive black holes, confining them into tight, focused beams that can stretch for millions of light years. They also act as colossal traps and accelerators for cosmic rays. These high-energy particles, mostly protons and atomic nuclei, are not deflected by electric fields because they are charged, but they are immensely susceptible to magnetic fields. As a cosmic ray travels through the galaxy, the interstellar magnetic fields bend its path, causing it to spiral around the field lines in a chaotic journey. This makes pinpointing the origin of any single cosmic ray nearly impossible, as its trajectory is a tangled mess by the time it reaches us. The fields effectively turn our entire galaxy into a massive particle accelerator and a labyrinth, hiding the sources of these mysterious travelers from our view. This invisible magnetic tapestry, born from the faintest whispers of the early universe and amplified by the motion of galaxies, is a fundamental force that silently orchestrates the structure and evolution of the cosmos we see. But if magnetic fields are the vast, invisible currents that guide cosmic structure, there is another quantum phenomenon operating on the smallest scales that is equally essential to our existence, a phenomenon so counterintuitive it allows particles to perform the impossible. This is quantum tunneling, and without it, the sun would never shine, and life as we know it would never have had a chance to evolve. In our everyday classical world, barriers are absolute. If you throw a ball at a wall, it bounces back. It doesn't mysteriously appear on the other side unless there's a hole or you throw it hard enough to break through. The quantum world, however, operates under a completely different set of rules. Here, particles are not just tiny balls, they are also waves, described by a probability wave function that defines the likelihood of finding them in any given location. And just as a sound wave can travel through a wall, albeit faintly, a particle's probability wave can extend into and even through a barrier that it classically shouldn't have the energy to surmount. There is a small but non-zero chance that the particle will simply appear on the other side, as if it had tunneled through an invisible passage. It doesn't punch a hole or expend energy. It literally cheats, leveraging the fundamental fuzzy uncertainty of the quantum realm. The mathematics that predicts this is both elegant and profound. The probability of tunneling depends on three key factors: the mass of the particle, the width of the barrier, and the height of the energy barrier itself. The equation reveals that for a light particle like an electron facing a thin, not too high barrier, tunneling can be a relatively common occurrence. For a heavier particle like a proton, or against a very wide or tall barrier, the probability drops off exponentially, becoming almost impossibly rare. This isn't magic, it's a direct and measurable consequence of the wave-like nature of all matter. Nowhere is the power of quantum tunneling more consequential than at the heart of every star. Our Sun is a massive fusion reactor, forcing hydrogen nuclei protons to overcome their tremendous mutual electrical repulsion and get close enough for the strong nuclear force to fuse them into helium. There's just one enormous problem. The energy required to overcome that repulsive barrier is far higher than the kinetic energy those protons possess at the Sun's core temperature of 15 million degrees. Classically, the Sun should not be able to shine. It is quantum tunneling that provides the solution. Even though the odds are incredibly small for any single pair of protons, the sheer number of collisions happening every second inside the Sun means that a tiny fraction of them will tunnel through the barrier. This slow, steady trickle of tunneling events is what sustains the Sun's fusion engine, providing the warmth and light that has nurtured life on Earth for billions of years. Every photon of sunlight that touches your skin is therefore a direct product of a quantum miracle. This same process is also responsible for the radioactive decay of certain unstable atomic nuclei like uranium through a mechanism called alpha decay. An alpha particle, 2 protons and 2 neutrons, is held inside the nucleus by the strong nuclear force, but it is trapped behind a formidable energy barrier. Classically, it should be stuck forever, yet its probability wave extends beyond the confines of the nucleus, and given enough time, it can tunnel out, causing the nucleus to decay. This process heats the interior of our planet and is a key power source for nuclear reactors. Our understanding of this effect has also led to some of humanity's most transformative technologies. The Scanning Tunneling Microscope, or STM, is a brilliant application of quantum tunneling. It uses an incredibly sharp metallic tip that is brought to within a nanometer of a sample surface. At that minuscule distance, the probability waves of electrons from the tip and the sample begin to overlap, allowing a tunneling current to flow. The strength of this current is exquisitely sensitive to the distance between the tip and the sample. By scanning the tip across the surface and maintaining a constant current, the instrument can trace the atomic contours of the material, literally allowing us to see and manipulate individual atoms. This invention revolutionized materials science, nanotechnology, and biology, giving us a direct window into the atomic world. The same principle is at work in the flash memory that stores data in your phone, USB drives, and solid-state hard drives. In these devices, electrons are made to tunnel through a thin, insulating barrier to become trapped on a tiny floating gate, where they can be stored for years, representing a single bit of digital information. Erasing the data involves making the electrons tunnel back out. This entire multi-billion-dollar industry is built upon our ability to precisely control the quantum tunneling effect. Some theoretical physicists have even ventured to propose that quantum tunneling might play a role in the most complex system we know of, the human brain. Certain theories of quantum consciousness suggest that processes like tunneling could be involved in the function of neurons and the nature of thought itself, though this remains a highly speculative and controversial frontier of science. Whether it fuels the stars, empowers our technology, or even touches the nature of our minds, quantum tunneling stands as a testament to the fact that the universe is not governed by classical rules of impossibility, but by a deeper, more nuanced quantum logic where probability reigns supreme. While quantum tunneling gives us the stars and powers our technology, it also opens the door to one of the most theoretically terrifying concepts in all of physics: the potential for our entire universe to be fundamentally unstable. This isn't about an asteroid impact or a solar flare. This is about the laws of physics themselves being suddenly and irrevocably rewritten. This brings us to the harrowing possibility of vacuum decay, a cosmic doomsday scenario that begins not with a bang but with a quantum whimper. The entire premise rests on the idea that the universe might not be in its true, lowest energy state. Think of our current vacuum not as a flat, stable plane, but as a valley perched high in the mountains. This valley is comfortable and stable for now. It's what we call a false vacuum. But somewhere out there, in the true bedrock of reality, lies a much deeper valley, a state of true vacuum with far lower energy. The terrifying part is that our entire universe, all of space and everything in it, is sitting in that higher valley. And just like a ball on a hillside, any system will naturally seek out the lowest possible energy state. The only thing preventing our universe from rolling down into that deeper valley is an energy barrier, a kind of quantum hill separating the false vacuum from the true one. This is where quantum tunneling re-emerges on a cosmic scale. We know that particles can tunnel through barriers they shouldn't be able to. In the same way, a random quantum fluctuation somewhere in the universe could cause a tiny, subatomic bubble of true vacuum to spontaneously form, tunneling through that energy barrier. Once this bubble is born, the laws of physics inside it are immediately and permanently different. The fundamental constants that govern reality, the strength of gravity, the mass of an electron, the nature of the nuclear forces, would be reconfigured into their new, stable state. The rules that allow atoms to form, stars to burn, and life to exist would be utterly erased. The true horror lies in what happens next. This bubble of true vacuum would not sit still. The energy difference between the false vacuum outside and the true vacuum inside creates an immense negative pressure, causing the bubble's wall to expand in all directions at the speed of light. As it expands, it converts the unstable false vacuum ahead of it into the stable true vacuum behind it, releasing a colossal amount of energy in the process. There would be no warning, no signal, and no escape. One moment, the universe is as it always was. The next, an expanding sphere of ultimate transformation is upon you, traveling at the universal speed limit. From our perspective, we would see nothing. The wall of the bubble would rewrite the laws of physics at the same moment it arrives, and the very processes needed to form a thought or register a sensation would cease to exist. The entire observable universe would be systematically and permanently altered, not with destruction, but with a chillingly silent redefinition of reality itself. A natural and deeply unsettling question arises. If this is possible, why hasn't it happened in the nearly 14 billion years since the Big Bang? Physicists have a few answers, though they are more statistical than comforting. The first is that the probability of such a tunneling event occurring in any given cubic meter of space over the age of the universe might be astronomically, unimaginably small. The energy barrier could be so high and so wide that the odds are effectively zero for our entire cosmic horizon. Another possibility is that it has already happened elsewhere, in regions of space so far beyond our observable universe that the expanding bubble hasn't had time to reach us yet. In an infinite or near-infinite cosmos, vacuum decay could be ongoing in other domains, its light-speed wave of transformation simply too distant to yet be a threat. This leads to a sliver of hope. Could we see it coming? In theory, if such an event were triggered a safe distance away, we might detect its approach. The leading edge of the bubble might be preceded by a faint, telltale signature of high-energy particles or radiation generated by the violent phase transition at its boundary. However, by the time our most sensitive instruments registered that anomaly, the bubble itself would be mere moments away, traveling at the speed of light. There would be no time to react, no time to understand, and certainly no time to escape. Our only real hope is that the universe is, in fact, in its true vacuum state already, or that the lifetime of our false vacuum is so long that it dwarfs any conceivable timescale we could measure, a number so vast it makes the age of our universe seem like a single, fleeting heartbeat. The study of vacuum stability, primarily through precise measurements of the Higgs boson and top quark masses, is an active and critical field of research, an effort to determine if our cosmic valley is truly secure or if we are all living on borrowed time. This seemingly impossible fine-tuning of the universe brings us to a principle that attempts to make sense of it all, a concept that sits at the crossroads of physics, philosophy, and metaphysics, the anthropic principle. In its simplest form, the anthropic principle is the observation that the universe we are capable of observing must be compatible with the existence of observers. We are here to see it, so it had to have properties that allowed for that to happen. It sounds almost trivial, but this simple statement has profound implications when applied to the dozens of physical constants that had to be set within an impossibly narrow range for life to ever arise. Scientists and philosophers generally discuss two main versions of this idea. The weak anthropic principle is the less controversial one. It's essentially a selection effect. It states that we must find ourselves in a universe capable of sustaining life, because in a universe that wasn't, we wouldn't be around to notice. It doesn't explain why the constants are right. It just acknowledges that our very existence as observers filters the kind of universe we can possibly perceive. We couldn't find ourselves in a universe that instantly collapsed after the Big Bang or one where atoms never formed, because such places are sterile and empty. The weak anthropic principle is a useful constraint, a tool that reminds us that our observations are not random but are biased by the necessity of our own existence. Then there is the strong anthropic principle, which takes a much more speculative leap. It proposes that the universe must have properties that allow life to develop within it at some stage in its history. This version suggests a sense of inevitability or purpose, that the laws of physics are in some way compelled to lead to conscious observers. This is where the principle often leaves the solid ground of testable science and ventures into more philosophical territory, sometimes being interpreted as evidence for a designer or some form of teleology, a built-in direction or goal for the cosmos. For many scientists, this strong version is deeply unsatisfying because it risks halting further inquiry by stating that things are the way they are because they had to be for us. To escape this philosophical trap and find a more scientific footing, some theorists have proposed fascinating mechanisms that could explain the fine-tuning without invoking anything supernatural. One of the most mind-bending is the concept of cosmological natural selection proposed by physicist Lee Smolin. His idea draws a direct parallel with Darwinian evolution. Smolin suggests that the interior of every black hole could be the seed for a new, offspring universe, and that with each new universe the fundamental constants might be randomly tweaked or mutated. Universes that have constants leading to prolific black hole production would have more children, while those with constants hostile to black hole formation would be evolutionary dead ends. Over countless generations, this cosmic evolution would naturally select for universes with physical laws that are optimized for making black holes, and it just so happens that the same constants that favor lots of black holes, like a specific strength for gravity and nuclear forces, also happen to be the ones that allow for long-lived stars, planets, and ultimately life. In this view, we don't live in a designed universe. We live in a universe that is the product of a grand multi-billion-year evolutionary process, and our existence is a fortunate byproduct of its fertility. The anthropic principle in all its forms remains fiercely controversial. Its supporters see it as a necessary and profound insight, the only logical framework for dealing with the staggering improbability of our existence. Its detractors argue that it is a mere tautology, a statement that is true by definition but explains nothing, or worse, unscientific speculation that can be used to justify any outcome after the fact. The key challenge is testability. Can we use the anthropic principle to make predictions, or does it only serve to explain what we already see? Some believe the multiverse concept provides that testable framework. If an infinite number of universes exist with different physical laws, then it is no surprise that we find ourselves in one of the rare, life-permitting ones. While we cannot yet visit these other universes, some theories predict that if our universe is one bubble in a vast multiverse, it might have collided with another bubble in the distant past, leaving a potentially detectable imprint on the cosmic microwave background. The search for such an imprint is an active, if speculative, area of research. Whether one sees it as a deep truth or a clever cop-out, the anthropic principle forces us to confront the sheer unlikelihood of our reality. It challenges our place in the cosmos not as a predetermined outcome, but as a contingent fact, one possibility among a near infinity of silent, lifeless alternatives. It suggests that the answers to the deepest questions of existence might not be found solely in the laws of physics within our universe, but in the nature of the vast, possibly infinite, reality beyond it. While the previous forces we've explored shape the cosmos on a grand scale, from the vacuum of space to the fabric of space-time, perhaps the most intimate and profound unseen force is the one you are using right now to ponder these very ideas, consciousness itself. For centuries, the nature of consciousness has been the domain of philosophers and poets, but a small group of scientists and theorists are proposing a radical idea: that the mysterious transition from mere neural computation to subjective experience might be explained by one of the most powerful and counterintuitive forces in the universe, quantum mechanics. This is the highly controversial realm of quantum consciousness. The most famous proposal in this field is the orchestrated objective reduction theory, or ORCH, put forward by the renowned physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their theory begins with a bold premise: that consciousness is not simply an emergent property of complex computation in the brain's neural networks, akin to software running on the wetware of the brain. Instead, they argue that the seat of consciousness lies deeper at the quantum level within the very structure of our neurons. Specifically, they point to structures called microtubules. These are intricate, lattice-like protein scaffolds that form part of the cell's cytoskeleton, providing structural support and acting as intracellular highways for transporting molecules. In neurons, microtubules are exceptionally abundant and organized. Penrose and Hameroff propose that these microtubules are far more than cellular scaffolding. They are quantum processors. Here's how their extraordinary theory unfolds. Within the microtubules, certain molecules could exist in a state of quantum superposition, a delicate state where they are in multiple states or positions simultaneously, a hallmark of the quantum world. Penrose had previously theorized that such a superposition would be inherently unstable. He proposed that the weighty difference between the multiple states would cause the superposition to eventually collapse or reduce to a single, definite state due to its own gravity, a process he called objective reduction. This collapse, according to the theory, isn't random. It's influenced by the underlying geometry of spacetime itself. Each collapse event is a moment of proto-consciousness. Hameroff then added the orchestration part, the idea that the brain's biological processes, its chemistry and neural connections, orchestrate these quantum activities, synchronizing them into a cohesive flow. In this view, our stream of consciousness is not a digital computation but a symphony of countless, orchestrated quantum collapses happening within the microtubules of our neurons. Naturally, a theory this revolutionary has faced immense and rigorous criticism from the broader scientific community. The primary objection is the environment itself. The brain is considered the last place you would expect to find delicate quantum coherence. It is warm, wet, and noisy, an environment where quantum superpositions are expected to decohere or fall apart almost instantly due to interactions with surrounding molecules. Critics argue that any quantum state in a microtubule would be disrupted far too quickly to have any meaningful impact on neural processes, which operate on millisecond timescales. Many neuroscientists also maintain that conventional approaches, which view the brain as a complex classical computer, are sufficient to explain consciousness without invoking unproven quantum effects. For them, or is an elegant solution in search of a problem, an unnecessary complication that lacks direct experimental evidence. Yet, just as the theory seems to hit a wall of skepticism, a fascinating field of science emerges to offer a surprising glimmer of plausibility: quantum biology. For a long time, it was assumed that quantum effects could only be observed in highly controlled, ultra-cold laboratory settings. But life itself appears to be using quantum mechanics to its advantage. The most well-documented example is in photosynthesis. Plants, algae, and some bacteria use complex molecular arrays to capture light energy from the sun and funnel it to a reaction center with near-perfect efficiency. Experiments have shown that this incredible efficiency is due to quantum coherence. The energy, in the form of an exciton, doesn't just randomly bounce along a path. It can explore multiple pathways through the photosynthetic complex simultaneously via quantum superposition, effectively finding the most efficient route to its destination. This isn't happening near absolute zero. It's happening in sunlight at room temperature. Another stunning example is found in the navigation of migratory birds. Species like the European robin travel thousands of miles with pinpoint accuracy, and they appear to use the Earth's faint magnetic field as a guide. The leading hypothesis for this magnetoception involves a quantum effect. It's thought that a light-sensitive protein called cryptochrome in the bird's eyes harbors a pair of electrons that become entangled. Their quantum spin state is influenced by the orientation of the Earth's magnetic field, and this quantum information directly affects the chemistry of the protein, ultimately providing the bird with a sensory perception of magnetic direction. Again, this is a delicate quantum process operating reliably in a warm, living system. These discoveries in quantum biology are revolutionary because they demonstrate that evolution has indeed found ways to harness quantum mechanics in warm, wet, and noisy biological environments. The brain, with its sophisticated structures and protective layers, could potentially be another such environment. If a plant can use quantum superposition to optimize energy transfer, and a bird can use quantum entanglement to see Earth's magnetic field, then is it truly impossible that the human brain might have evolved its own quantum tricks to generate the phenomenon of consciousness? The door, while certainly not open wide, is now undeniably cracked. The debate over quantum consciousness forces us to confront the deepest questions about the nature of reality and our place within it, suggesting that the line between the objective physical world and our subjective inner experience might be far more blurred and far more quantum than we ever dared to imagine. If the quantum world challenges our notions of reality, then the next idea shatters them completely, proposing that the universe we perceive might be nothing more than an elaborate illusion, a cosmic mirage. This is the holographic principle, a concept so radical it suggests that all the information describing our three-dimensional reality, every star, every planet, and every one of us, is actually encoded on a distant, two-dimensional surface that surrounds us. We are not just in the universe, we might be a projection of it, a hologram of breathtaking complexity. The seeds of this astonishing idea were not planted in the study of illusions, but in the most concrete and paradoxical objects in the cosmos, black holes. In the 1970s, physicist Jacob Bekenstein made a profound discovery. He realized that a black hole's event horizon, the point of no return, has entropy. Entropy is a measure of disorder or, more fundamentally, of information content. This was shocking because it meant a black hole wasn't just a simple, featureless pit. It had a hidden complexity related to the amount of information it had swallowed. Stephen Hawking later showed that black holes radiate energy and slowly evaporate, which created a terrifying puzzle known as the information paradox. If a black hole evaporates completely, what happens to all the information about the stars, planets, and particles that fell into it? The fundamental laws of quantum mechanics state that information cannot be destroyed. The holographic principle emerged as a stunning solution. The principle boldly states that all the information contained within any volume of space can be fully described by the information stored on the boundary of that region. For a black hole, everything that ever fell in is not lost inside the singularity. It is painted like a fossil record on the surface area of its event horizon. This was a complete inversion of how we think. We intuitively believe that the information capacity of a room depends on its volume, how much stuff you can pack inside. But the holographic principle says no, it depends on the area of the walls. This implies a fundamental limit to the information any region of space can hold, and that our perception of a third dimension is a kind of emergent property, a decoding of a two-dimensional data set. This abstract concept found a rigorous mathematical foundation in 1997 through the work of physicist Juan Maldaisner. He discovered the anti-de Sitter/conformal field theory correspondence, or ADS/CFT. This is a concrete realization of the holographic principle within string theory. In simple terms, Maldaisner showed that a gravitational theory operating in a hypothetical higher dimensional space with a certain curvature, called anti-de Sitter space, is completely equivalent to a quantum field theory without gravity operating on its lower dimensional boundary. It's a dictionary that translates problems in a complex, hard-to-solve gravitational universe into simpler, gravity-free problems on its surface. This correspondence is now a cornerstone of theoretical physics, providing a powerful tool for exploring everything from the behavior of black holes to the properties of exotic states of matter. But if this is true, could we ever find evidence for it in our own universe? Scientists are not content to leave this as a mathematical curiosity. They are designing experiments to hunt for hints that we are living in a hologram. The key prediction is holographic noise. If space-time is fundamentally pixelated, emerging from a two-dimensional reality, then at the tiniest possible scale, the Planck scale, it should have a subtle granularity or jitter. This wouldn't be noise in the usual sense, but a fundamental fuzziness in the fabric of reality itself. Experiments like the holometer, an incredibly sensitive laser interferometer, have been built to search for this jitter. By looking for correlated noise in its beams that cannot be explained by any known standard model physics, it aims to detect the literal pixelation of spacetime. While definitive proof remains elusive, the very attempt to measure this effect transforms the holographic principle from a philosophical mind game into a testable scientific hypothesis. This idea forces a complete rethink of existence. It suggests that the tangible, three-dimensional world we experience, the feeling of depth, the solidity of objects, the vastness of space, is a magnificent illusion generated from an immense cosmic code written on the farthest horizon of the universe. We are not just made of atoms, we are made of information. The universe is not a collection of things, but a projection of data, a cosmic story being read, and in that reading we are brought to life. But if our reality is a holographic projection, the underlying cosmic code must have been written by something during the universe's first moments, and the process might not have been perfectly smooth. This leads us to another staggering relic that could be woven into the very fabric of spacetime itself: cosmic strings. These are not strings in the sense of tiny vibrating filaments from string theory, but vast, incredibly thin defects in the structure of the cosmos, like cracks frozen in ice when water freezes too rapidly. They are thought to be leftovers from a dramatic phase transition in the universe's earliest, superheated infancy, mere fractions of a second after the Big Bang. To understand how such an object could form, think of water cooling and turning to ice. As it freezes, the water molecules align into a crystal structure. If the cooling happens very uniformly, the ice can form a perfect, clear crystal. But if it cools rapidly and unevenly, defects like cracks and fissures get trapped inside. The universe underwent a similar process as it expanded and cooled from an unimaginably hot, dense state. The various fundamental forces, electromagnetism, and the strong and weak nuclear forces, are now distinct, but physicists believe they were once unified into a single superforce. As the cosmos cooled, this unified force went through a series of phase transitions, breaking apart into the separate forces we know today. It's during these splits, these cosmic moments of symmetry breaking, that imperfections could have been created and then stretched to astronomical sizes by the universe's rapid inflation. Cosmic strings are one such hypothetical imperfection, infinitely long, or forming closed loops with a thickness of perhaps just a proton but a mass of incredible density, potentially millions of tons per centimeter. The gravitational influence of such an object would be bizarre and dramatic. A cosmic string wouldn't pull matter towards it with a standard gravitational field like a planet or star. Instead, its immense mass would warp the space around it in a very specific way, creating a conical defect. Imagine taking a piece of paper and cutting out a thin pizza slice wedge, then taping the remaining edges together. The surface is still flat, but it now has a sharp angle missing. Space around a cosmic string would be similar. This unique geometry leads to a startling optical effect: gravitational lensing. If a string passed between us and a distant galaxy, the warped space would act like a prism, bending the light and potentially creating not one, but two identical mirror image copies of the same galaxy in the sky, a perfect double without the distortion typical of lensing by a spherical mass. The dynamics of these strings could also be a potent source of the gravitational waves we've only recently begun to detect. While black hole and neutron star mergers create brief, transient chirps, a network of cosmic strings would generate a continuous background hum of gravitational radiation. Kinks and cusps that develop as strings oscillate and vibrate at near light speed would send out powerful bursts of these space-time ripples, potentially detectable by future observatories. Furthermore, their presence in the early universe would have subtly influenced the cosmic microwave background, the afterglow of the Big Bang. The unique way a string would affect the temperature and polarization of this radiation could leave a faint linear signature, a telltale scratch on the oldest photograph of the cosmos that astronomers are actively searching for. Despite these clear observational signatures, we have not yet definitively found a cosmic string. Their elusive nature is part of the challenge. They could be exceedingly rare, with only a few within our entire observable universe, or their predicted gravitational effects might be weaker than initially theorized. Another possibility is that the energy scale of the phase transitions that formed them was different, making the strings too faint for our current telescopes and sensors to pick up. Their role in structure formation is also a subject of fascinating theoretical work. In some models, these cosmic defects could have acted as gravitational seeds around which the first galaxies condensed, providing an alternative or complementary mechanism to the quantum fluctuations from inflation. The search for them continues, a hunt for the cracks in creation that would provide a direct window into the universe's most violent and formative moments, proving that even its smoothest structures might be built upon ancient hidden flaws. But what if there was a structure that broke not just spatial symmetries, but the most fundamental symmetry of all, the symmetry of time itself? This brings us to one of the most bizarre and groundbreaking discoveries in modern physics: time crystals. A time crystal is not a glittering mineral that measures hours and minutes. It is an entirely new phase of matter, the first to break time translation symmetry. In our everyday experience, the laws of physics are the same at every moment. If you perform an experiment today and again tomorrow, assuming the same conditions, you should get the same result. The system is symmetric in time. A time crystal shatters this expectation. It is a quantum system that oscillates or ticks in a stable, repeating pattern without any energy input. It's a clock that winds itself, a perpetual motion machine not of the impossible classical kind, but one that operates within the strange rules of the quantum world. The concept was first proposed in 2012 by the Nobel laureate Frank Wilczek. He wondered if, just as a regular crystal has atoms arranged in a repeating pattern that breaks the spatial symmetry of empty space, there could be a system whose ground state, its lowest energy configuration, breaks time symmetry by exhibiting periodic motion. The initial idea was met with significant skepticism, as it seemed to challenge fundamental thermodynamic principles. How could something oscillate forever without losing energy? The resolution to this paradox lies in the quantum nature of the system. A true time crystal isn't creating energy from nothing. It's in a protected quantum state where its motion is locked in, immune to the friction and decay that would quickly stop any macroscopic pendulum. Turning this theory into reality required immense ingenuity. The first experimental realizations didn't create a single, large crystal you could hold, but rather microscopic time crystals in highly controlled quantum systems. One of the first successful creations used a line of ytterbium ions trapped by electric fields and manipulated with precise lasers. The researchers would kick this system, much like tapping a bell to make it ring. A normal system would eventually quiet down, its ringing fading as energy dissipates, but the time crystal did something remarkable. It began ringing at a different frequency than the kick. This subharmonic response, a beat that exists only because of the system's own internal quantum structure, was the signature of a discrete time crystal. It was ticking to its own quantum rhythm. Another approach used a dense collection of nitrogen vacancy defects in diamond atomic imperfections where a nitrogen atom sits next to a missing carbon atom. When manipulated with microwaves, this system also exhibited the telltale persistent oscillation, confirming that this new phase of matter was not just a theoretical fantasy. The potential applications of this discovery are as profound as they are futuristic. The most immediate impact could be in the field of quantum computing. Qubits, the fundamental units of quantum information, are notoriously fragile, easily losing their delicate quantum state through a process called decoherence. A time crystal, with its inherent stability and resistance to external perturbations, could act as a perfect quantum memory device, a robust platform for storing quantum information that is protected by its own topological structure. Furthermore, the precise clock-like oscillation of time crystals could be used to create incredibly accurate sensors for measuring magnetic fields or time itself, far surpassing the capabilities of current atomic clocks. Beyond the practical, time crystals force us to confront deep questions about the nature of time and the laws of thermodynamics. They exist in a state of persistent non-equilibrium, a system that never settles into a boring, static state but is forever dancing between configurations. This reveals a rich new landscape of matter that exists out of equilibrium, governed by rules we are only beginning to decipher. They hint that the arrow of time, which always points toward increasing disorder, might have more nuanced behaviors in the quantum realm. A time crystal doesn't defy entropy. It finds a loophole, a stable and orderly pattern that can persist within a universe relentlessly driving toward chaos. It is a testament to the endless creativity of physical law, showing us that even a concept as fundamental as time can exhibit structures and symmetries we never dreamed possible. These cosmic strings, remnants of a broken symmetry, and time crystals, structures in time itself, stretch our conception of what is possible. But what if the reality they inhabit is not the only one? What if our entire cosmos, with all its laws and constants, is just a single page in an infinite library of existence? This brings us to one of the most expansive and debated ideas in all of science and philosophy, the multiverse. The concept that our universe is not alone, but merely one member of a vast, perhaps infinite, ensemble of universes, each with its own unique physical laws and history. The first and perhaps most supported version of this idea arises directly from the theory of cosmic inflation. As we discussed, inflation is the period of exponential expansion thought to have shaped our early universe. But many models suggest that once inflation starts, it may be eternal. In this breathtaking scenario, the inflatoned field, the engine of expansion, doesn't stop everywhere at once. While it decayed in our patch of space to end inflation and create our Big Bang, quantum fluctuations would cause it to continue expanding exponentially in other regions. Each place where inflation ends becomes a separate bubble universe, isolated from all the others within the ever-inflating background. Each of these bubbles would have its own Big Bang and could potentially have different physical constants depending on how the fields within it settled. In this inflationary multiverse, new universes are constantly being born, creating a growing cosmic foam of realities forever beyond our observable reach. A second, even more complex vision comes from string theory. To unify gravity with the other forces, string theory requires extra spatial dimensions, tiny, curled-up shapes at every point in space. The physics we observe, the properties of particles and the strengths of forces, depend critically on the geometry of these curled-up dimensions. The shocking discovery was that there are a staggering number of possible stable configurations for these dimensions. Estimates range from 10 to the 500 up to 10 to the 2,000 different possibilities. This vast collection of potential universes is known as the string theory landscape. The inflationary multiverse might then be the mechanism that populates this landscape, with each bubble universe representing a random roll of the cosmic dice, landing on one specific set of dimensions and thus one set of physical laws. In this view, the reason our universe's constants seem so finely tuned for life isn't due to purpose or design, but simply because we exist in one of the rare bubbles where the dice roll allowed for our existence. In the unimaginably vast multiverse, every possibility is realized somewhere. A third type of multiverse arises not from cosmology but from the interpretation of quantum mechanics itself, the many worlds interpretation. Proposed by Hugh Everett in the 1950s, it offers a radical solution to the infamous measurement problem, the puzzle of why we only ever see a single, definite outcome from a quantum system that exists in multiple superimposed states. Everett's daring suggestion was that the superposition never collapses. Instead, at the moment of a quantum event, like measuring the spin of an electron, the entire universe splits into multiple branches. In one branch, the observer measures spin up. In another, completely separate branch, an identical observer measures spin down. Both outcomes are real, but they become forever separated in the ever-branching wave function of reality. In this multiverse, every possible outcome of every quantum event actually occurs, leading to an infinite tree of diverging timelines. There is a universe where you never watched this video, and another where you are already an expert on these topics, all existing in a vast, unobservable superposition. Finally, there is the most speculative and all-encompassing idea, the mathematical multiverse, championed by thinkers like Max Tegmark. This proposal suggests that every mathematically consistent structure actually exists as a physical reality. If a set of equations describes a logically coherent universe, then it is out there somewhere. This idea removes physics entirely from the equation. Existence is not dependent on physical laws but on mathematical consistency. Our universe isn't special because it has the right constants for life. It's simply one particular mathematical structure that contains self-aware subsystems that are capable of observing it. The fundamental challenge with all multiverse theories is their scientific status. Can they be tested, or do they remain in the realm of philosophical speculation? Critics argue that if these other universes are permanently causally disconnected from our own, if no signal, light, or influence can ever cross from their realm into ours, then the multiverse concept is not falsifiable and therefore not scientific. It becomes a metaphysical assumption. Proponents, however, point to potential indirect tests. For the inflationary multiverse, if our bubble universe collided with another in the distant past, it could have left a unique, anisotropic imprint on the cosmic microwave background, a kind of cosmic bruise that we might one day detect. For the string theory landscape, if we could somehow determine that the laws of our universe are but one possibility in a larger landscape, it would lend powerful indirect support. The search for any evidence of these ideas is one of the most ambitious and controversial frontiers in physics, a quest to determine if we are the sole authors of our cosmic story or merely one sentence in a library of infinite tales. Throughout this journey, we've seen how gravity warps space-time and how quantum mechanics governs the subatomic realm. Yet these two pillars of modern physics are fundamentally at odds, describing a universe that operates by two completely different sets of rules. Reconciling this schism is perhaps the single greatest challenge in all of physics, a quest to find a theory of quantum gravity that can seamlessly weave them into a single, coherent tapestry of reality. The heart of the conflict lies in their core principles. General relativity paints a beautiful picture of gravity as the smooth, continuous curvature of space-time, a flexible stage upon which the cosmic drama unfolds. Quantum mechanics, on the other hand, reveals a particle world that is granular, probabilistic, and subject to wild, unpredictable fluctuations. When we try to apply the equations of quantum field theory to the smooth fabric of space-time, the math completely breaks down, producing nonsensical answers of infinite energy and probability. It becomes clear that to understand the most extreme environments in the cosmos, like the infinitely dense singularity at the heart of a black hole or the very first moment of the Big Bang, we need a new physics that can marry these two incompatible worlds. One of the most prominent and elegant approaches to this unification is string theory. This framework makes a radical proposal. The fundamental constituents of the universe are not point-like particles but incredibly tiny, vibrating one-dimensional strings. Each distinct vibration mode of a string corresponds to a different particle. One mode might give us an electron, another a photon, and another a graviton, the hypothetical quantum particle that would carry the gravitational force. This is the theory's great triumph. It naturally includes gravity within its quantum mechanical description. Furthermore, string theory requires extra spatial dimensions for its mathematical consistency. Not just the 3 we experience, but 6 or 7 more, all curled up into a space so small we can't perceive them. The specific way these dimensions are folded determines the properties of the particles and forces in that universe, potentially explaining the values of nature's constants. However, string theory faces significant challenges. It has a vast number of possible solutions, perhaps 10 to the 500 or more, leading to a dizzying landscape of potential universes. This makes it difficult to find the one solution that uniquely describes our own. More critically, the energy scales required to directly test string theory are far beyond the reach of any particle accelerator we could ever build, pushing potential experimental verification into the distant future. In direct opposition to string theory's approach stands loop quantum gravity. If string theory tries to unify all forces by building them from strings, loop quantum gravity takes a more minimalist path, focusing solely on quantizing gravity itself. It proposes that spacetime is not smooth and continuous, but is instead composed of tiny, discrete, indivisible loops, a fabric woven from a network of finite threads. Picture the fabric of reality not as a seamless silk sheet, but as a pixelated image, with each pixel being a minuscule volume of space. This granular structure becomes apparent only at the unimaginably small Planck scale. In this theory, the familiar smooth spacetime of general relativity emerges as an average of these fundamental quantum grains. Much like water appears continuous even though it is made of individual molecules. One of loop quantum gravity's most stunning predictions is the elimination of the Big Bang singularity. Instead of a point of infinite density, the theory suggests a big bounce, where a previous universe contracted to a small size before quantum gravity effects caused it to rebound into our expanding cosmos. While conceptually beautiful and avoiding the need for extra dimensions, loop quantum gravity has its own struggles, particularly in showing how a smooth spacetime reliably emerges from its quantum foundations and how it might connect to the other forces of nature. A third, less well-known but equally fascinating approach is causal dynamical triangulation. This theory takes a hands-on, computational strategy to visualize the quantum structure of spacetime. Imagine building the universe out of tiny, simple building blocks, in this case, 4-dimensional triangular shapes called simplices. The rules are simple. These blocks must be connected to each other in a way that preserves causality, meaning cause must always precede effect within each connection. Using powerful supercomputers, researchers randomly assemble billions of these tiny blocks and then apply the laws of quantum mechanics to the entire structure to see what large-scale shape emerges from the chaos. Astoundingly, these simulations consistently show that a 4-dimensional universe, just like our own, spontaneously arises from the random connections. At large scales, the smooth, continuous spacetime of general relativity appears, while at the tiniest scales, the fabric of reality becomes a chaotic, fractal foam. This approach provides a concrete, visual way to study the quantum properties of gravity, though it too has yet to make a definitive, testable prediction that could confirm its validity. The central frustration for all these theories is the immense difficulty in testing them. The energy required to probe the Planck scale directly is about a quadrillion times greater than what the Large Hadron Collider can achieve. Without the ability to experiment directly, how can we ever know if we're on the right track? The answer may lie in the cosmos itself, using the universe as our ultimate laboratory. Primordial gravitational waves, the faint ripples in spacetime from the inflationary period just after the Big Bang, could carry an imprint of quantum gravity. If these waves can be detected, their polarization might reveal clues about the quantum nature of gravity in the universe's first moments. Similarly, the enigmatic event horizon of a black hole presents another testing ground. Stephen Hawking's work showed that black holes should radiate energy and slowly evaporate, but this creates the infamous information paradox. What happens to the information about the matter that fell in? How quantum gravity resolves this paradox could reveal its true character. Perhaps information is encoded on the event horizon and slowly released, or maybe it tunnels into a baby universe. The solution will undoubtedly require a full theory of quantum gravity, and observing the final moments of an evaporating black hole, though far beyond our current capabilities, would provide the ultimate test. Until then, the quest continues, a grand intellectual adventure to uncover the deepest law of nature, the fundamental rule that wrote all the others. While our previous forces dealt with grand cosmic structures and the fabric of spacetime, our next unseen actor operates on the smallest of scales, a ghost that passes through our planet by the trillions every second without a single trace. These are neutrinos, and their bizarre behavior holds a secret that cracked open the foundation of modern physics. Born in the nuclear fires of the Sun, in the heart of supernova, and even in the core of our own nuclear reactors, these particles are the ultimate escape artists, interacting with matter so rarely that most will fly through the entire Earth as if it weren't even there. For decades, the standard model of particle physics, our most successful theory of the fundamental forces, considered them to be massless, weightless travelers moving at the speed of light. But then, we noticed something impossible. They were changing their identity right before our eyes, a phenomenon known as neutrino oscillation. To understand this, picture a neutrino not as a single, static particle, but as a quantum chameleon that exists in a constant state of flux. The three types or flavors we know are the electron neutrino, the muon neutrino, and the tau neutrino, each named for the charged particle they are associated with. Now, imagine a neutrino is created in the Sun's core as an electron neutrino. According to the old rules, it should remain an electron neutrino for its entire existence. But as it travels the 93 million miles to Earth, a strange quantum metamorphosis occurs. The particle we call a neutrino is not a pure flavor state, but is actually a mixture of three different mass states. As these mass states travel, they evolve at slightly different rates due to their different masses. By the time the neutrino reaches our detectors, this internal quantum interference has reshuffled the mixture, giving it a calculable probability of being detected as a muon or tau neutrino instead of the electron neutrino it started as. It's as if a strawberry started its journey from the farm, but by the time it reached your kitchen, there was a significant chance it had transformed into a blueberry or a raspberry. The first major clue for this came from a profound puzzle known as the solar neutrino problem. Experiments built to catch neutrinos from the Sun, like the legendary Homestake Mine experiment led by Ray Davis, consistently found only about 1/3 of the number predicted by our most detailed models of solar fusion. For years, physicists were baffled. Was our understanding of the Sun wrong, or was something strange happening to the neutrinos on their way here? The revolutionary answer was provided by the Sudbury Neutrino Observatory in Canada, a brilliant detector that used 1,000 tons of heavy water to be sensitive to all three neutrino flavors. Their results were definitive. The total number of neutrinos arriving from the Sun matched the predictions perfectly. The missing electron neutrinos hadn't vanished, they had simply oscillated into the other flavors which previous experiments couldn't see. The Sun was producing the right number, we just needed to learn how to count them all. Simultaneously, another mystery was unfolding with neutrinos created in our own atmosphere. When cosmic rays smash into the upper atmosphere, they create showers of particles including muon and electron neutrinos. Detectors like the famous Super Kamiok and in Japan could tell the direction these neutrinos came from. They found that muon neutrinos coming straight down from the sky above arrived in the expected numbers, but those coming up through the Earth from the atmosphere on the far side of the planet were only half as abundant. The explanation was the same. The neutrinos that had traveled the longer distance through the Earth had more time to oscillate into tau neutrinos, which the detector couldn't observe at the time. These two independent discoveries from the Sun and the atmosphere provided irrefutable proof that neutrinos were oscillating and therefore must have mass, a finding so monumental it was awarded the Nobel Prize in Physics in 2015. This revelation, while spectacular, is deeply disruptive. The minimalist Standard Model had no room for massive neutrinos. Their tiny but non-zero mass is the first incontrovertible evidence of physics operating beyond that brilliantly successful but incomplete theory. It forces us to ask what other particles or forces might be waiting to be discovered that could explain the origin of neutrino mass. The implications are staggering, potentially linking to the mystery of why our universe is made of matter and not antimatter. This leads us to the next frontier of neutrino physics, the hunt for a violation of charge parity symmetry, or CP violation, in the neutrino sector. Just as a slight asymmetry in the behavior of quarks is thought to have helped shape the matter-dominated universe we live in, a similar asymmetry in neutrinos could be the dominant reason we exist at all. Massive international experiments are now underway to chase these ghosts and their secrets. Projects like the Deep Underground Neutrino Experiment in the United States will fire a powerful beam of neutrinos through 800 miles of the Earth's crust to a colossal detector filled with liquid argon, meticulously measuring how the beam changes flavor over that distance. Other endeavors, like the Hyper Kamiok and detector in Japan, will use a tank of water so vast it could hold multiple Olympic-sized swimming pools to watch for neutrinos from supernova, the atmosphere, and man-made beams. The ultimate goal is to pin down the precise masses of the three neutrinos and measure the degree of CP violation in their oscillations. Finding a significant asymmetry would be a landmark discovery, providing a plausible mechanism for how the early universe could have favored the creation of matter over antimatter, ultimately allowing galaxies, stars, planets, and us to form. These elusive, shape-shifting particles, once thought to be mere spectators in the cosmic drama, are now guiding us toward a deeper, more complete law of nature. But if the universe began in a blaze of near-perfect uniformity, as the cosmic microwave background suggests, then why does this baby picture of the cosmos seem to contain a bizarre, improbable axis, a mysterious alignment that appears to point a finger directly at us? This brings us to one of the most perplexing and controversial large-scale anomalies in all of cosmology, a finding so strange it's been dubbed, with a hint of dramatic irony, the axis of evil. This story begins with our most detailed map of the universe's infancy, the Planck satellite's exquisitely precise measurement of the cosmic microwave background. These tiny temperature fluctuations on the order of 1/100,000th of a degree are the seeds from which all galaxies and clusters would eventually grow. According to our foundational cosmological principle, these fluctuations should be random and evenly distributed across the sky. The universe should have no preferred direction, no center, and no edge. It should look the same in all directions, yet when cosmologists began analyzing the very largest patterns in this map, the fluctuations on scales broader than our entire galactic horizon, they noticed something deeply unsettling. These gigantic, whisper-quiet ripples appeared to be aligned. They weren't randomly oriented, they seemed to define a specific axis running through the cosmos, and this axis was curiously correlated with the plane of our own solar system and the direction of the Sun's motion through space. The statistical unlikelihood of this is staggering. Imagine throwing a bucket of paint at a massive blank canvas. You would expect the largest splatters to be randomly distributed, pointing in every conceivable direction. Now imagine that upon close inspection, the biggest splashes all somehow aligned along a single, straight line that also, incredibly, points toward the spot where you were standing when you threw the paint. The probability of such an alignment happening by pure chance in the cosmos is less than 1 in 1,000, a clear red flag that something in our standard model might be profoundly wrong. This apparent alignment directly challenges the cosmological principle, the bedrock assumption upon which almost all of modern cosmology is built. If the universe has a preferred axis, a kind of cosmic north, then it is not the same in all directions, and we are, in some sense, in a special place. Naturally, the first and most prudent suspicion fell on systematic error. Could this axis be an illusion, a ghost in the machine created by our own methods? Perhaps the way we subtract the foreground glow of our own galaxy is imperfect, leaving behind a subtle contaminant that mimics a pattern. Maybe there's an unknown source of interference within our solar system, or even a previously unaccounted for effect from the solar wind. Researchers have spent years meticulously testing and retesting these possibilities, refining their data processing to an astonishing degree, yet the anomaly persists. While some of the smaller-scale oddities in the CMB have faded with better data, this large-scale alignment has stubbornly refused to be wiped away, remaining one of the most significant and puzzling outliers in our cosmic dataset. If it's not an error, then we are left with two breathtaking and frankly unsettling possibilities. The first is that we are indeed seeing the imprint of physics from a time before the Big Bang, a relic from the pre-inflationary universe. Inflation is supposed to have erased any such primordial structure, stretching it to undetectable smoothness. But if this axis is real, it could be a cosmic fossil, a scar from a time before inflation began, a structure so vast that not even the incredible stretching of inflation could completely wipe it clean. It would be a window into the unknown physics of the universe's absolute beginning, a place where our current laws of physics may completely break down. The second possibility is even more radical. It could be evidence for a multiverse. In the eternal inflation scenario, our universe is one bubble in a vast, frothing cosmic foam of universes. These bubbles might not be completely isolated. They could potentially collide. If a neighboring universe brushed up against ours in the distant past, the immense energy of that collision would have left a distinct imprint on the edge of our cosmic bubble, an imprint that might manifest as a preferred direction or axis in the CMB. In this view, the axis of evil isn't a flaw in our universe. It's a bruise from a run-in with a parallel reality, a signpost pointing toward a cosmos vaster and stranger than we ever imagined. Whether a data ghost, a cosmic fossil, or a multiverse bruise, the axis of evil remains an open wound in our understanding of the universe. It is a powerful reminder that our most cherished principles are not dogma, but working models, always subject to revision by the next great observation. It humbles us, suggesting that even our most objective map of the cosmos might still, in some subtle way, be reflecting our own place within it. Yet for all their power to warp spacetime and trap light, black holes present a paradox that strikes at the very heart of physics, a conflict so deep it questions our fundamental understanding of reality. This is the black hole information paradox, and it begins with what seems like a simple question. What happens to the information about an object when it falls into a black hole? According to Einstein's general relativity, the answer is straightforward. An object crossing the event horizon would be stretched and compressed by the immense tidal forces, eventually adding to the mass, charge, and spin of the black hole. The only three properties a black hole is supposed to have. All the other intricate details, what the object was made of, whether it was an encyclopedia or a heap of dust, the story of its creation, seemed to be utterly erased, lost forever inside the singularity. This presents no problem for classical physics. The crisis emerged when Stephen Hawking applied quantum mechanics to the curved spacetime around a black hole. He made the startling discovery that black holes are not completely black. Due to quantum fluctuations near the event horizon, pairs of virtual particles can pop into existence. Normally, these pairs would annihilate each other almost instantly, but if this happens right at the edge of the event horizon, one particle can fall in while the other escapes into space. To conserve energy, the particle that falls in must have negative energy, which reduces the mass of the black hole. The escaping particle becomes real, carrying away a tiny bit of the black hole's energy. This stream of escaping particles is Hawking radiation. Over immense timescales, this process causes the black hole to slowly evaporate, eventually vanishing entirely. Here lies the paradox. Hawking radiation is thermal radiation. It's random and featureless, depending only on the black hole's mass, charge, and spin. It contains no information whatsoever about the countless stars, planets, and books that fell in. So when the black hole finally evaporates, all that detailed information is seemingly lost forever. This violates a sacred principle of quantum mechanics, unitarity. Quantum mechanics is deterministic and reversible. Information can never be truly destroyed. If you know the final state of a completely burned book, you should, in principle, be able to work backwards to deduce every word that was on its pages. Hawking's calculation suggested that black holes irrevocably burn the book of the universe, making its story forever unrecoverable. This set up a direct conflict, a choice between the bedrock of quantum theory and the predictions of general relativity, a crisis known as the information paradox. For decades, physicists argued over this. Hawking himself initially believed information was indeed lost, famously making a bet with other physicists that it was. But the tide began to turn as researchers delved deeper into the holographic principle. If a black hole's interior can be fully described by information encoded on its event horizon, its two-dimensional surface, then the information about infalling matter isn't actually plunging into a mysterious interior. It is smeared and stored on the horizon itself like a cosmic fingerprint. When Hawking radiation is emitted, it must somehow carry that information away, imprinted in subtle correlations between the radiated particles. The black hole's evaporation would then be like burning a book, but having its entire text encoded in the precise pattern of the smoke rising from the flames. The information is not lost, it is transformed and eventually released, preserving the quantum rulebook. This elegant solution, however, gave birth to a new and even more ferocious paradox, the firewall paradox. Imagine you are an astronaut falling feet first into a large black hole. According to Einstein's principle of equivalence, which is the foundation of general relativity, you should feel nothing special as you cross the event horizon. It is not a brick wall in space, but rather a one-way door you pass through without noticing. The spacetime around you should be smooth and empty, but now consider the holographic view. If the information from every object that ever fell in is stored on the horizon, that region is actually a seething, energetic membrane encoding an astronomical amount of data. For the information to be released in the Hawking radiation, the horizon must be highly excited, a chaotic mess of high-energy particles. From the perspective of an outside observer watching you fall in, you would appear to be incinerated instantly at the horizon by a blazing wall of fire, a firewall, contradicting the smooth spacetime predicted by Einstein. So we are left with a brutal either-or choice. Either the infalling astronaut is vaporized at the horizon, saving quantum mechanics but violating general relativity, or they pass through peacefully, saving general relativity but forcing us to accept that information is somehow cloned, another quantum taboo, as the same information exists both inside the black hole and on the horizon. Both options shatter a fundamental pillar of modern physics. The firewall paradox suggests that our understanding of either quantum theory or gravity is profoundly incomplete, and that reconciling them will require a revolution. Current research is focused on this razor's edge, and the most promising path forward involves the very subject we explored earlier, quantum entanglement. The key may be that the entanglement connections between particles inside and outside the black hole become violently disrupted during the evaporation process. This transfer of entanglement from between the inside and outside to now being between the early and late Hawking radiation might create the enormous energy required for a firewall, or alternatively, reveal a more subtle mechanism where the horizon only appears fiery from one perspective while remaining smooth from another. Resolving this paradox is not an academic exercise. It is a direct probe into the quantum nature of spacetime itself. The answer will likely illuminate how the three-dimensional world we experience emerges from a deeper, two-dimensional reality, finally revealing the true architecture of a theory of quantum gravity and showing us how the universe truly keeps its deepest secrets. While black holes and cosmic axes present puzzles on the grandest scales, sometimes the most telling clues come from our own backyard, from the subtle, unexpected behavior of the very spacecraft we send out from Earth. This brings us to a mystery that baffled orbital dynamicists for over 3 decades, the Pioneer anomaly. In the vast, predictable clockwork of the solar system, where the motions of planets and moons follow Newton and Einstein's rules with incredible precision, the Pioneer 10 and 11 probes were doing something they shouldn't. They were ever so slightly slowing down. Launched in the early 1970s, the twin Pioneer spacecraft were trailblazers, the first to journey through the asteroid belt and the first to make close-up observations of Jupiter and Saturn. After completing their planetary missions, they continued on trajectories that would eventually carry them out of the solar system entirely. As they cruised through the void, scientists back on Earth meticulously tracked their positions using the Doppler shift of their radio signals. By measuring the tiny changes in the frequency of these signals, they could calculate the probe's velocity with astonishing accuracy, and that's when they noticed the glitch. Both spacecraft were experiencing a constant sunward deceleration of about 8.74 times 10 to the negative 10th meters per second squared. It was an incredibly small effect, equivalent to slowing down by just 1 centimeter per second every year and a half, but it was persistent, unexplained, and it didn't align with any known gravitational model. For years, this tiny discrepancy was a thorn in the side of physics. Could it be evidence of a flaw in our understanding of gravity? Some speculated about the influence of unseen dark matter in the solar system, or perhaps a modification to the laws of gravity itself at very weak accelerations. The possibility that we were on the verge of a revolutionary discovery, a new physics hiding in the motion of our own probes, was electrifying. The anomaly became one of the most debated topics in fundamental physics, a classic example of how the most precise measurements can reveal the most profound secrets. The solution, when it finally came, was not a rewriting of the laws of physics, but a triumph of meticulous, patient detective work. A dedicated team of researchers embarked on a years-long effort to recover old telemetry data and build incredibly detailed thermal models of the Pioneer spacecraft. Their hypothesis was elegant: heat. The plutonium in the probe's radioisotope thermoelectric generators decayed, producing heat that was converted into electricity to power the spacecraft. The waste heat from this process, about 2,500 watts, was radiated into space, but the spacecraft were asymmetrical. Their large dish antennas acted as shields, reflecting more of this thermal radiation off their backsides than their fronts. This created a tiny but constant recoil force pushing back against the direction of travel, a photon brake gently applying the brakes on the Pioneers. When the team finished their painstaking analysis, the numbers matched almost perfectly. The anomalous acceleration was explained not by dark matter or new gravity, but by the subtle, unaccounted-for push of photons. It was a lesson in humility and a testament to the fact that in the complex, real world, even the smallest systematic effect must be considered before proclaiming a revolution. However, the closure of the Pioneer case doesn't mean all such mysteries are solved. Other spacecraft, like the Galileo probe sent to Jupiter and the European Rosetta mission that rendezvoused with a comet, have shown their own tiny, unexplained orbital deviations. These are often different from the Pioneer effect and remain without a definitive answer. This tells us that the universe is still testing our ability to measure and model reality with absolute precision. Every one of these anomalies, whether eventually explained by conventional physics or not, serves as a crucial stress test for our theories. They force us to refine our models to account for every last watt of heat and every subtle non-gravitational force, pushing our engineering and computational skills to their absolute limits. This relentless pursuit of precision is how we ultimately uncover the truly new physics. By eliminating all known explanations, we are left with only the truly inexplicable. Future missions designed with these lessons in mind will be even more stable, their trajectories even more precisely tracked. As we send probes farther into the unknown, this exquisite control allows us to use them as the most sensitive gravity detectors imaginable, testing whether Einstein's general relativity holds perfectly over ever greater distances. The ghost of the Pioneer anomaly reminds us that discovery often doesn't begin with a bang, but with a whisper, a faint, persistent signal in the data that refuses to go away, nudging us toward a deeper understanding of the cosmos. But if our most fundamental theory of reality is a quantum one, a realm of shimmering possibilities and multiple states existing at once, then why does the world we actually experience feel so solid, so definite, and so classical? Why do we only ever see a single, unambiguous outcome? This is the infamous measurement problem, the central schism at the heart of quantum mechanics, and it leads us to a compelling and elegant theory for how the subjective becomes objective: quantum Darwinism. For decades, the prevailing explanation was the Copenhagen interpretation, which essentially said that the very act of measurement by a conscious observer forces the quantum wave function to collapse into a single state. But this has always felt deeply unsatisfying. It places consciousness outside of physics, creating a mysterious and arbitrary dividing line between the quantum and classical worlds. Quantum Darwinism, pioneered by Wojciech, offers a far more natural and robust solution, one that doesn't require an observer at all. Instead, it places the power of selection squarely in the environment itself. The core idea is breathtakingly simple. The classical world emerges not through conscious observation, but through a process of natural selection for quantum information. The environment acts as a constant, relentless measuring device, and the quantum states that are most effectively copied and disseminated by the environment are the ones we perceive as real. To understand how this works, imagine a single quantum system, like an atom that can be in a superposition of two states, say, spinning both clockwise and counterclockwise simultaneously. Now, this atom doesn't exist in isolation. It's surrounded by an environment of countless particles, photons, air molecules, dust motes. As these environmental particles bounce off the atom, they interact with it and gather information about its state. But here's the crucial part: they can only reliably copy information about a specific set of quantum states. These special states are called pointer states, and they are uniquely robust, able to withstand the decohering effect of the environment without being disrupted. In our atom example, the pointer state might be a definite spin direction rather than a fragile superposition of both. When a photon scatters off the atom, it doesn't record a blur of both spins, it records a specific classical outcome. That photon then flies away, carrying that information out into the world. This is where the Darwinian selection occurs. The pointer states are the fittest because they produce the most redundant copies of themselves in the environment. A single quantum system will be probed by trillions upon trillions of environmental particles, each one leaving with a nearly identical story about the system's pointer state. This creates a multitude of imprints, a kind of consensus reality broadcast across the environment. for any larger system, whether it's a measuring apparatus or a human brain, to find out the state of the quantum system. It doesn't need to directly interact with the fragile quantum object itself. It simply has to sample a small fraction of the environment. It's like trying to learn about a famous painting. You don't need to go to the Louvre and see the Mona Lisa in person. You can look at a poster, a postcard, a digital image, or read a description in a book. The information has been redundantly copied and is widely available. The environment provides many identical, classical-looking views of the quantum system, and it is this redundancy that creates objective reality. We all agree on the state of a chair because the information about the chair's position has been copied and disseminated by trillions of photons reflecting off it, creating a consensus that our senses can easily access. This framework elegantly solves the measurement problem without any spooky collapse or appeal to consciousness. The wave function doesn't collapse, it decoheres. The environment selectively entangles with the pointer states, and the interference terms that allow for quantum weirdness leak out into the environment, becoming irretrievably lost and impractical to recover. What remains for us to observe is a stable, classical-looking world. Quantum Darwinism also makes a specific, testable prediction. The degree of objectivity of a property should be directly proportional to the amount of information about that property that is available in the environment. Experimentalists are now designing intricate setups to test this, using quantum systems to probe how information about a central qubit is redundantly imprinted on a surrounding cloud of other qubits acting as the environment. Early results are promising, showing that the predicted redundancy does indeed emerge, lending strong support to this revolutionary view of how our tangible reality precipitates out of the quantum fog. For all the precise clockwork we see in the motions within our solar system, when we zoom out to the scale of the entire cosmos, a far more turbulent and mysterious flow emerges. Galaxies are not simply drifting apart with the expansion of the universe. They are also rushing together in immense rivers of matter, pulled by gravity on the grandest scales. And our Milky Way, along with our entire local group of galaxies, is caught in one of these mighty cosmic currents, heading toward a destination we cannot see, pulled by a force whose true nature remains hidden. This is the Great Attractor, a gravitational anomaly of staggering proportions that has challenged astronomers for decades. Our journey to this discovery began not with a direct image, but by carefully mapping the peculiar velocities of galaxies, their motions over and above the smooth expansion of the universe. By the 1970s and 80s, surveys were revealing a startling large-scale flow. Our galaxy is moving at an incredible 600 kilometers per second relative to the radiation left over from the Big Bang. A huge portion of this motion was toward the dense constellations of Centaurus and Hydra. Something immense in that direction was pulling us, along with thousands of other galaxies, in a vast sheet of matter now called the Laniakea supercluster. But when astronomers pointed their optical telescopes toward that part of the sky, they couldn't see the source of this tremendous pull. The culprit was located directly behind the plane of our own Milky Way, in a region astronomers call the zone of avoidance. This zone is not a void, it is the most crowded and obscured part of our sky. The disk of our galaxy is thick with interstellar gas and dark dust that blot out visible light from beyond, and it is crowded with countless stars that make it incredibly difficult to pick out distant background galaxies. It is like trying to see a distant mountain range through a dense, blinding fog. For a long time, this region was a literal blind spot in our map of the universe, perfectly positioned to hide the most significant gravitational landmark in our intergalactic neighborhood. To pierce this veil, astronomers had to turn to telescopes that see the universe in different wavelengths of light. Infrared surveys, like those from the 2-micron all-sky survey, can peer through the dust to reveal many galaxies that were previously hidden. But the real breakthrough came from radio astronomy. Hydrogen gas, the primary component of interstellar space, emits a characteristic radio signal at a wavelength of 21 centimeters. By tuning radio telescopes to this frequency, astronomers could map the distribution of neutral hydrogen gas in galaxies hidden behind the Milky Way's dust, effectively seeing them not with light, but with the radar ping of their most abundant element. This painstaking work began to reveal the skeleton of a colossal structure lurking in the zone of avoidance. What they found was not a single, unimaginably massive object, but a tremendous concentration of mass known as the Norma cluster, which acts as the heart of a much larger supercluster. This entire region, now identified as the core of the Great Attractor, is an immense gravitational well containing the mass of tens of thousands of galaxies. Yet, even this enormous collection of matter seems insufficient to fully account for the observed motion of our local group. This has led scientists to propose that the Great Attractor itself is merely a waypoint, a signpost on a much longer journey. The true source of the pull may lie even farther beyond, in an incomprehensibly vast concentration of mass known as the Shapley supercluster, the largest known structure in our local universe. So the Great Attractor may not be a final destination, but rather a major milestone on a cosmic highway, with the gravitational tug of Shapley acting as the prime mover behind the scenes. Ongoing efforts to map these dark regions continue with more powerful instruments, each new dataset refining our understanding of this hidden geography. The story of the Great Attractor is a powerful lesson in cosmic humility. It reminds us that our view of the universe is often limited by our own vantage point, and that the most powerful forces shaping our cosmic journey can be hidden in plain sight, waiting for the right technology and ingenuity to reveal them. While the universe is pulled by immense gravitational flows and shaped by quantum rules, there is a fundamental stability to the ordinary matter that makes up our world. The desk you're sitting at, the screen you're watching, even your own body, they aren't changing their fundamental composition from one moment to the next. The protons at the heart of every atom are seemingly eternal, and this stability is the very reason anything exists at all. But what if this permanence is an illusion? What if even the proton, the bedrock of material reality, is destined to eventually fade away? This is the startling prediction of many grand unified theories, and the relentless, decades-long search for its evidence brings us to our next unseen force, the potential for proton decay. For a long time, the absolute stability of the proton was a foundational rule in physics, enshrined in the conservation of baryon number. A baryon is a category of particles that includes protons and neutrons, and this law stated that the net number of baryons in the universe must always remain constant. You can't just create or destroy a proton, it has to be part of a balanced equation. This rule worked perfectly within the standard model of particle physics. But when physicists began developing theories to unify the electromagnetic, weak, and strong nuclear forces into a single grand unified theory, or GUT, this rule came crashing down. These elegant theories propose that at extremely high energies, trillions of times beyond what our most powerful colliders can produce, these three forces merge into one, and a stunning consequence emerges. In this unified framework, a quark, the building block of a proton, can transform into a lepton like an electron or a positron. This transformation would violate baryon number conservation and mean that the proton is no longer stable. It must, given enough time, decay into lighter particles. The predicted timescale for this process is beyond human comprehension, which is why we never notice it in everyday life. Different GUTs predict different half-lives, but a common prediction settled on a value of around 10 to the 34 years. To put that in perspective, the current age of the universe is only 13.8 billion years, or 10 to the 10 years. A 10 to the 34-year half-life means that if you were watching a tank containing 10 to the 34 protons, you would expect to see just one of them decay per year. Catching such an impossibly rare event requires a monumental experiment. This led to the creation of some of the most impressive underground laboratories in the world. To shield from the constant rain of cosmic rays that would create false signals, detectors were built deep within mountains and abandoned mines. The most famous of these is the Super Kamiok, an experiment in Japan, a colossal cylindrical tank nestled a kilometer underground, filled with 50,000 tons of ultra-pure water and lined with 13,000 incredibly sensitive light detectors called photomultiplier tubes. The principle is to wait and watch. If a single proton inside one of the water's oxygen atoms were to decay, the resulting particles would travel faster than the speed of light in water, producing a faint but telltale flash of blue Cherenkov radiation. The pattern of this light would be the unmistakable fingerprint of a proton's demise. After decades of continuous, meticulous observation, Super K and other experiments like it have yielded a profound result: nothing. Not a single confirmed instance of proton decay has ever been observed. This null result is itself one of the most significant discoveries in modern physics. It has forced the predicted half-life to be pushed out to at least 10 to the 35 years, ruling out the simplest and most elegant grand unified theories. The universe has told us that the proton is even more stable than we thought, creating a major crisis for theoretical models that sought to simplify the forces of nature. This incredible stability is not just a curiosity, it is deeply connected to one of the greatest mysteries in cosmology. Why does our universe contain so much matter and almost no antimatter? The Big Bang should have created equal amounts of both, which would have annihilated each other, leaving behind a sea of pure radiation and nothing else. The fact that we exist means some process must have favored matter over antimatter by the tiniest fraction. This required violation of baryon number conservation. Proton decay is the experimental key to testing this idea. If a proton can decay, it proves that baryon number is not a sacred law, providing a crucial mechanism that could have operated in the early universe to create the matter-antimatter imbalance we see today. The fact that we haven't seen it decay yet means the specific mechanism proposed by many JUTs is wrong, sending theorists back to the drawing board to devise more complex and subtle theories, such as those involving supersymmetry or extra dimensions, which might predict an even longer proton lifetime that is still just beyond our current reach. The silent, dark water of Super Kamiok, and is therefore listening for more than just the death of a particle. It is listening for the answer to why we are here at all. Yet for all the grand structures and fundamental particles we've explored, perhaps the most unsettling paradox of all doesn't require a galaxy or a proton. It requires only a single, disembodied mind spontaneously blinking into existence in the void. This is the bizarre thought experiment known as the Boltzmann brain, a concept that uses the fundamental laws of thermodynamics to challenge everything we assume about consciousness, memory, and reality itself. The paradox is named for Ludwig Boltzmann, the 19th century physicist who helped pioneer statistical mechanics. He realized that the second law of thermodynamics, which states that entropy always increases, isn't an absolute rule but a statistical one. A system tends toward disorder simply because there are vastly more ways to be disordered than to be ordered. But given enough time, random fluctuations will occasionally create order from chaos. Imagine a box filled with gas. The most probable state is for the molecules to be evenly distributed, a state of high entropy. But it's not impossible for all the molecules to randomly and simultaneously bounce into one corner of the box, creating a moment of unexpected order. The math of statistical mechanics tells us that if you wait long enough, this incredibly rare event will eventually happen. Now, take this principle and apply it to the largest possible canvas, the entire universe. In a vast, near-empty space that has reached maximum entropy, a cold, dark, and uniform void, a random thermal fluctuation could, in principle, assemble anything. Given an almost infinite amount of time, the atoms and particles drifting in the void could spontaneously arrange themselves into a fully formed, conscious brain, complete with false memories of an entire life it never lived. This brain would, for the brief moment before it dissolved back into chaos, believe itself to be a person sitting somewhere, reading a book, or even watching a video about the mysteries of the cosmos, with no way to tell that its entire experienced reality was a fleeting statistical accident. This idea moves from a curious footnote to a profound crisis when we consider certain models of cosmology, particularly eternal inflation. If our universe is just one bubble in an infinite, eternally inflating multiverse that has existed forever, then the timescales involved become not just long but truly infinite. In such a cosmos, the number of Boltzmann brains randomly fluctuating into existence would, according to the math, vastly outnumber the number of ordinary brains that evolved naturally within stable universes like our own. This leads to a terrifying statistical conclusion. If this cosmological model is correct, then you are far more likely to be a lonely, disembodied brain hallucinating a universe for a nanosecond than you are to be a real person in a real, enduring cosmos. Your feeling that you've lived a continuous life is merely a perfectly detailed but completely false memory generated by the fluctuation. Most physicists view this not as a plausible reality, but as a powerful reductio ad absurdum, a logical argument that demonstrates the absurdity of its premise by showing it leads to an absurd conclusion. The fact that we are clearly not Boltzmann brains, that we observe a coherent, consistent universe with a verifiable past, is taken as strong evidence that the cosmological models that predict we should be Boltzmann brains must be flawed. The paradox acts like a canary in a coal mine for theories of eternal inflation, forcing cosmologists to refine their models to avoid this bizarre prediction. It suggests that the universe cannot be infinitely old in the way these models propose, or that there is some other physical mechanism that prevents such fluctuations from being the dominant form of consciousness. The Boltzmann brain is ultimately less about brains and more about the nature of reality and observation. It's a stark reminder that our theories of the cosmos must ultimately account for the fact that we, as observers, exist within it in a stable, ordered way, and that any theory that makes our own existence seem statistically miraculous is probably pointing us toward a deeper truth we have yet to uncover. Yet for all the intricate evidence supporting dark matter, a small but dedicated group of physicists has been pursuing a radically different path, one that questions not the contents of the universe but the very law of gravity itself. This alternative framework is known as modified Newtonian dynamics, or MUND, and it proposes a breathtakingly simple idea. Perhaps we haven't found dark matter because it doesn't exist. Instead, our understanding of gravity is incomplete, especially in the realm of the very faint, where accelerations become incredibly weak. The theory was first proposed by Israeli physicist Mordechai Milgrom in the early 1980s, directly inspired by the puzzle of galaxy rotation curves. Instead of invoking an invisible halo of matter to explain why stars on the outskirts of galaxies move too fast, Milgrom suggested a modification to Newton's second law. He proposed that gravity ceases to follow the familiar inverse square law when accelerations drop below a certain critical threshold, a very small value of about 100 billionth of a meter per second squared. Above this threshold, physics operates as Newton and Einstein described, but below it, gravity experiences a tiny boost, providing the extra pull needed to keep those high-speed outer stars from flying away. With just this single new constant, MUND achieved something remarkable. It could accurately predict the rotation curves of a huge variety of spiral galaxies without a single particle of dark matter. The observed motion of the stars was not evidence of missing mass, but of a new regime of physics that only manifests itself in the dim, sparse outskirts of galaxies. This predictive power is MUND's greatest strength. It is not a theory that is constantly tweaked to fit new galactic data. In many cases, it successfully predicted the rotation velocity of a galaxy based solely on the distribution of its visible mass. For its proponents, this elegance is a powerful sign that they are on the right track, arguing that dark matter models often require complex and fine-tuned explanations for the behavior of individual galaxies. Mund suggests a universal law that applies cleanly across the board. However, this elegant solution for individual galaxies runs into formidable challenges when faced with the broader cosmos. The first major hurdle is the behavior of galaxy clusters. When astronomers observe huge clusters of galaxies, they see three independent signs of mass: the visible light from stars, the X-ray emission from incredibly hot gas trapped in the cluster's gravity, and the gravitational lensing effect that reveals the total mass. In a Mund universe, the visible mass should be enough to account for the gravity. Yet, the observed lensing and the pressure of the hot gas show a clear mass discrepancy. The cluster simply has more gravity than Mund can provide with its visible contents. To salvage the theory, some researchers have suggested that clusters might still contain a small amount of non-luminous conventional matter, perhaps in the form of neutrinos with a small amount of mass. This begins to look suspiciously like, though on a much smaller scale, the dark matter it seeks to replace. The most devastating blow to a pure Mund theory, however, comes from cosmology. The single most powerful evidence for dark matter is the cosmic microwave background, the baby picture of the universe. The precise patterns of hot and cold spots in this radiation are a fossil record of sound waves traveling through the primordial plasma. The characteristics of these waves, their spacing and amplitude, depend critically on the composition of the universe. The observed pattern matches a model where dark matter makes up about 27% of the cosmos with astonishing precision. A universe without dark matter, where ordinary matter is the only gravitational player, produces a pattern that looks nothing like what we see. Furthermore, the ability of dark matter to seed the formation of galaxies and the vast cosmic web is a success story that Mund, in its original form, cannot replicate. It excels at explaining the end product of finished galaxy, but struggles to describe the process of how that galaxy gathered its mass in the first place. The quest to overcome these hurdles has led to the development of relativistic versions of Mund theories that aim to replace not just Newtonian gravity, but Einstein's general relativity itself. The goal is to create a complete theory that can explain both the dynamics of galaxies and the large-scale structure of the universe. The most prominent of these is TVS, or tensor vector scalar gravity, developed by Jacob Bekenstein. This theory introduces additional fields alongside the metric of spacetime to produce the Mund behavior. While TVS can reproduce some aspects of Mund and has had some success with gravitational lensing, it has struggled to fully match the exquisite detail of the cosmic microwave background data and has introduced its own theoretical complexities. Other, more recent proposals are also being explored, but creating a theory that is as universally successful as the dark matter paradigm remains an immense challenge. The story of Mund is not a tale of a failed idea, but a vital dialogue in the scientific process. It acts as a necessary provocateur, forcing the dark matter community to sharpen its theories and make more precise, testable predictions. It reminds us that our grasp of the fundamental laws of nature is always provisional, and that the greatest mysteries often require us to question our most basic assumptions. Whether Mund eventually evolves into a complete theory or remains a powerful insight into galactic dynamics, its legacy is secure. It ensures that our search for the truth remains rigorous, creative, and open to all possibilities. Now imagine yourself floating in the deep, empty void of space. To you, the vacuum is just that, a silent, empty void, completely devoid of particles. But what if you suddenly hit the accelerator? If you began accelerating faster and faster, your experience of this nothingness would transform in a way that seems almost miraculous. you would suddenly find yourself surrounded by a warm bath of particles glowing with heat. This isn't a malfunction of your sensors, it's a real effect predicted by quantum field theory. To an observer moving with constant velocity, the vacuum remains empty. But to you, the accelerating observer, the void has come alive. This bizarre phenomenon is known as the Unravel effect, named after the physicist William Unravel who discovered it, and it reveals a deep and unsettling truth. The very concept of a particle depends entirely on your state of motion. At the heart of this effect lies a profound connection to the Hawking radiation that evaporates black holes. Both phenomena stem from the same quantum principle. The vacuum of space is not truly empty. It is a seething foam of virtual particles constantly blinking in and out of existence. For an inertial observer, these fluctuations average out to zero, a perfect balance of creation and annihilation. But an accelerating observer cuts through this quantum foam in a way that disrupts this delicate balance. The relentless acceleration effectively prevents the observer from seeing the virtual particle pairs annihilate each other perfectly. What was a fleeting, virtual fluctuation for a stationary observer becomes a real, detectable particle for the accelerating one. The temperature of this perceived particle bath is directly proportional to the acceleration. To experience a warmth of just 1 degree above absolute zero, you'd need an acceleration that is physically unimaginable, on the order of a quintillion times the force of Earth's gravity. This is why we don't notice it in everyday life, but in the most extreme environments it becomes a fundamental feature of reality. This incredible discovery is a direct consequence of Einstein's equivalence principle, the cornerstone of general relativity, which states that acceleration and gravity are indistinguishable. The Unravel effect provides a stunning quantum validation of this idea. The thermal glow you see while accelerating is fundamentally the same as the Hawking radiation a distant observer sees emanating from a black hole. In both cases, an event horizon is the key. For a black hole, it's the point of no return from which light cannot escape. For an accelerating observer, there is a different kind of horizon, a Rindler horizon. This is a boundary in space that, from your perspective as you accelerate away, information from beyond it can never reach you. It is this horizon that thermalizes the vacuum, converting quantum uncertainty into real particles. The Unravel effect essentially shows us the quantum nature of inertia itself, suggesting that the resistance we feel when we try to accelerate an object may be due to it interacting with this energetic vacuum bath. For decades, the Unravel effect was a fascinating but entirely theoretical prediction, as the accelerations required to produce a detectable temperature were far beyond any conceivable experiment. However, recent breakthroughs have opened up a potential path to verification. The key insight is that the effect isn't solely about raw acceleration, it's also about the timescale of that acceleration. If an electron can be subjected to an absolutely immense acceleration for just a minuscule fraction of a second, the Unravel effect could leave a detectable signature. The most promising avenue for this is within the focused fury of an ultra-intense laser field. When a high-power laser pulse interacts with a beam of electrons, it can accelerate those electrons so violently and so rapidly that they could, in theory, experience a fleeting glimpse of the Unravel glow. The challenge is isolating this signature from the overwhelming noise of other radiation, but clever experimental designs are being developed to do just that. Another fascinating proposal involves using circular accelerators like particle colliders, but in a novel way. While the constant centripetal acceleration in a collider is enormous, the direction of acceleration is always changing, which complicates the simple Unravel picture. Theorists are now exploring whether electrons circulating in a storage ring could experience a modified version of this effect, potentially allowing us to probe this quantum phenomenon with existing technology. Successfully detecting the Unravel effect would be a monumental achievement. It would provide direct experimental evidence for the particle creation process that powers black hole evaporation, solidify our understanding of the equivalence principle in the quantum realm, and open an entirely new window into the nature of inertia and acceleration, blurring the line between the quantum vacuum and the tangible world of particles we perceive. While we can map the faint afterglow of the Big Bang as the cosmic microwave background, there exists an even more ancient and elusive fossil permeating every inch of the cosmos, a whisper from a time before light could even travel. This is the cosmic neutrino background, and it holds secrets from the universe's very first second of existence. To understand its origin, we need to rewind the cosmic clock even further than we did for the CMB. Just 1 second after the Big Bang, the universe was an incredibly dense, seething soup of particles and energy. At this time, neutrinos were constantly interacting with protons, neutrons, and electrons, trapped in a tight, chaotic dance. But as the universe expanded and cooled at a ferocious rate, it very suddenly crossed a critical threshold. The energy of particles dropped too low for neutrinos to continue interacting effectively. In a cosmic instant, the universe became transparent to them. These ghostly particles decoupled from matter and began streaming freely across the expanding cosmos, never to significantly interact again. This event happened a full 380,000 years before the photons of the CMB were set free, making the neutrino background the oldest known fossil in the universe, a snapshot of reality from its first breathtaking second. These relic neutrinos are now everywhere. It's estimated that there are about 336 of these primordial neutrinos in every cubic centimeter of space, meaning trillions are passing through your body every second. But their energy is vanishingly small, having been stretched and cooled by the expansion of the universe to a temperature of just about 1.95 degrees above absolute zero, making them even colder than the CMB. This combination of their extremely weak interaction with matter and their incredibly low energy makes them perhaps the most difficult particles to detect in all of physics. We cannot simply build a bigger version of a neutrino detector like Super Kamiok, and these ancient neutrinos don't have enough energy to trigger the reactions those instruments are designed to catch. Detecting them requires a level of ingenuity that pushes the boundaries of experimental science. The hunt for this background is focused on a rare and specific type of event. The most promising method is to look for a process called inverse beta decay, but with a twist. If a relic neutrino were to, by an almost unimaginable chance, interact with a radioactive isotope that is undergoing beta decay, it could very slightly change the energy spectrum of the emitted electrons. The Ptolemy experiment, for example, proposes using a vast amount of tritium, a radioactive form of hydrogen coated onto a graphene sheet. The idea is to look for a tiny kink or bump in the spectrum of electrons released by the tritium's decay, a signature that would be caused by the neutrino background scattering off the decaying nuclei. It's like trying to hear a single, specific whisper in a roaring stadium by listening for the faint, unique echo it creates off one particular wall. Successfully capturing this signal would open a direct window into a period of the universe we can currently only theorize about. Because they decoupled so early, these neutrinos were present during the era of Big Bang nucleosynthesis, when the first atomic nuclei were forged. Their properties directly influenced how much hydrogen and helium was created in those first few minutes. By measuring the cosmic neutrino background, we could test our models of that pivotal epoch with unprecedented precision. Furthermore, it could finally answer one of the most pressing questions in neutrino physics: what is the absolute mass of the neutrino? While we know from oscillations that they have mass, we only know the differences between the masses, not the actual values themselves. The subtle way these relic neutrinos would interact in a detector is exquisitely sensitive to their absolute mass scale, potentially allowing us to weigh the universe's most elusive particle for the very first time. This ancient sea of ghosts is not just a cosmic relic. It is a hidden archive waiting to reveal the conditions of the universe's birth and the true nature of one of its most mysterious inhabitants. We stand before a chasm so vast it represents the single greatest failure of prediction in the entire history of science. It is a discrepancy so enormous it defies everyday analogy. Imagine calculating the height of a single sheet of paper, but your theory instead predicts a stack of paper tall enough to reach the Andromeda galaxy and back, not once but trillions upon trillions of times. This isn't a minor rounding error, it is a catastrophic breakdown in our understanding, and it lies at the very heart of the vacuum of space. This is the cosmological constant problem. Recall that the quantum vacuum is not a true nothingness, but a seething foam of virtual particles constantly flickering in and out of existence. Every cubic centimeter of empty space is alive with this activity. When physicists attempt to calculate the total energy density of this vacuum, to add up the energy contribution of every possible quantum fluctuation in every possible field, they arrive at a number. This number should correspond to the strength of dark energy, the force that is accelerating the expansion of the universe. The calculation is perhaps the most straightforward in modern physics, and the answer it gives is unequivocal. The vacuum energy should be about 10 to the 120 times larger than the value we actually observe from astronomical measurements. That is a 1 followed by 120 zeros. This isn't just the worst prediction in physics, it is the worst prediction in any field of inquiry ever. The sheer scale of this error suggests one of two incredible possibilities. Either we are the beneficiaries of an almost impossible cosmic coincidence, a cancellation of unimaginable precision, or there is something fundamentally and profoundly wrong with our understanding of how gravity and quantum mechanics interact. This has sent theorists scrambling for decades, proposing a zoo of potential solutions. One of the most elegant is supersymmetry. This theory posits that every known particle has a massive, undiscovered superpartner. The beautiful symmetry of this idea would cause the positive quantum contributions to the vacuum energy from ordinary particles to be perfectly cancelled out by the negative contributions from their superpartners. The vacuum energy would naturally settle at zero or very near it. The problem is we haven't found any of these superpartners despite extensive searches at the Large Hadron Collider. If they exist, they are far heavier than initially hoped, making this perfect cancellation much less natural. Other ideas are even more radical. Some physicists suggest that the vacuum energy isn't a fixed property of the universe but can actually decay over time, or perhaps it is dynamically set by a new, unknown field that is still evolving. Another fascinating proposal is that our understanding of gravity is simply wrong on the largest scales. Perhaps Einstein's theory of general relativity needs a subtle modification when applied to the cosmos as a whole, a tweak that would prevent the vacuum energy from gravitating in the way we expect, effectively hiding its immense predicted strength. Then there is the possibility that forces us to confront our place in the cosmos head-on, the anthropic principle within a multiverse. If the inflationary multiverse is real, then every bubble universe could have a randomly different value for the vacuum energy. In the overwhelming majority of these universes, the value is enormous. In those worlds, the repulsive force of dark energy is so violently strong that space rips itself apart instantly after the Big Bang, preventing any stars, planets, or the possibility of life from ever forming. We, of course, find ourselves in one of the exceptionally rare bubbles where the value is minuscule and non-lethal, allowing for the 13.8 billion years of evolution required for us to be here to observe it. In this view, there is no deeper reason for the small number. It is merely a statistical selection effect. We couldn't possibly observe any other value. Each of these solutions comes with its own heavy price. Supersymmetry is beautiful but so far unseen. Modifying gravity is incredibly difficult to do without breaking the many successful predictions of general relativity. And invoking a multiverse, while perhaps scientifically plausible, can feel to some like a philosophical retreat, an admission that we may never find a fundamental reason within our own universe for this critical number. The cosmological constant problem, therefore, remains the paramount puzzle in fundamental physics. It is a stark reminder that for all our knowledge, we are still gazing into the depths of reality with newborn eyes, staring at a number that holds the key to the universe's fate, yet whose origin remains utterly and completely unknown to us. But if even the vacuum of space is alive with unseen energy, then what role do we, as conscious observers, play in shaping the reality we perceive? This brings us to one of the most provocative and fiercely debated ideas at the frontier of physics: the possibility that consciousness itself is not a passive byproduct of the universe, but an active participant in its unfolding. This is the controversial proposition that the human mind might be directly entangled with the quantum world, playing a fundamental role in the mysterious transition from possibility to actuality known as the measurement problem. The most famous formulation of this idea is the von Neumann-Wigner interpretation, named after the two towering physicists who developed it. In his monumental mathematical foundation of quantum mechanics, John von Neumann laid out a chain of measurement. When a quantum system, like an atom in a superposition, interacts with a measuring device, the device itself should enter a superposition correlating with the atom. That device could be a Geiger counter, a photographic plate, or any other physical apparatus. But then, when a scientist reads the result from the device, their sensory organs and brain would also become entangled, theoretically entering a superposition of having seen all possible outcomes. So why do we, the conscious observer at the end of this chain, only ever perceive one definite result? Eugene Wigner took this logic to its ultimate conclusion. He argued that the chain of entanglement must be broken by something that exists outside the description of standard physics, and that something is consciousness. In this view, it is the irreducible act of conscious awareness that finally collapses the wave function, selecting one reality from the shimmering fog of possibilities. This interpretation stands in stark opposition to the now mainstream explanation provided by decoherence theory. As we explored with quantum Darwinism, decoherence explains the emergence of a classical world through interaction with the environment, not through conscious observation. The environment acts as a constant, relentless measuring device, rapidly dissipating quantum coherence and making superpositions practically impossible to detect at large scales. For the vast majority of physicists, decoherence provides a complete and physically grounded solution to the measurement problem, rendering the need for a conscious observer unnecessary. They argue that introducing consciousness into fundamental physics is a category error, mixing the objective with the subjective and halting scientific progress by invoking an unexplainable mystery to solve another mystery. Yet, the allure of a connection between mind and quantum mechanics persists, leading to modern variations and experimental ventures. Some researchers, often working at the intersection of quantum physics and cognitive science, have proposed designing experiments to test if conscious intention can directly influence quantum systems. One famous, though heavily criticized, series of experiments involved a double-slit setup where participants were asked to mentally will the quantum system to behave like a particle or a wave. The reported, though highly contested, results suggested a slight statistical deviation when focused intention was applied. Other theoretical models propose that consciousness is not the cause of collapse, but rather a specific kind of quantum process that arises from it, perhaps occurring in the microtubules of brain neurons as suggested by the Orch theory we discussed earlier. The overwhelming skepticism from the physics community toward these ideas is rooted in a fundamental principle of science: parsimony. Decoherence offers a mechanical, testable, and non-magical explanation for the quantum to classical transition. Introducing consciousness adds a layer of complexity that is, as of yet, utterly untestable in a rigorous, reproducible way. There is no known mechanism for how a thought or an awareness could physically interact with a quantum system to collapse its wave function. Furthermore, it creates a bizarre and unsatisfying picture of the early universe. If conscious observation is required for collapse, then what collapsed the wave function of particles in the eons before any life evolved? Did the universe exist in a bloated superposition of all possible states until the first conscious creature opened its eyes? Most scientists find this an untenable proposition, preferring a universe whose history is independent of its inhabitants. Ultimately, the idea that consciousness causes collapse remains firmly on the fringe of physics. Yet, its persistence speaks to a deeper, more philosophical yearning to understand our place in the cosmos. It challenges the strict materialist view and forces us to confront the hard problem of consciousness. Why should a particular configuration of matter experience the world subjectively at all? While the von Neumann-Wigner interpretation may not provide a scientific answer, it keeps a profound question alive, reminding us that the complete story of reality likely weaves together the objective and the subjective in ways we are only beginning to imagine. And so, as we reach the end of this cosmic journey, what has our exploration of these 30 unseen forces truly revealed? It shows us a universe that operates on a level of complexity and wonder far beyond the limits of our ordinary senses. We have traveled from the incomprehensible vastness of dark energy, relentlessly stretching the very fabric of space-time, down to the frenetic, probabilistic dance of the quantum vacuum, where particles flicker into and out of existence, moment by moment, building reality itself from the ground up. We have seen how gravity warps the stage upon which the cosmic drama unfolds, how invisible fields bestow mass upon matter, and how the universe might be a holographic projection of information stored on a distant, two-dimensional surface. This is not the simple, clockwork cosmos we once imagined. It is a living, breathing, and deeply mysterious entity, sculpted by forces we are only beginning to comprehend. The sheer number of these hidden mechanisms, the dark matter weaving galaxies together, the quantum entanglement linking particles across light years, the cosmic inflation that set everything in motion, paints a picture of a reality that is profoundly strange, yet governed by a beautiful, underlying order we can strive to understand. Pursuing this understanding is more than just an academic exercise. It is perhaps the most noble endeavor of our species. For in unraveling these cosmic secrets, from the stability of a proton to the potential instability of our vacuum, we are ultimately seeking answers to humanity's biggest and oldest questions. Why is there something rather than nothing? What is the nature of consciousness itself? And what is our true place in this grand, bewildering cosmos? Each of these 30 forces is a piece of that immense puzzle, a clue left for us to find. The most exciting part is that this story is still being written. The map is not finished. There are blank spaces waiting for the next great discovery, the next revolutionary idea that will once again transform our perception of reality. This conversation doesn't end here. We want to know what you think. Which of these unseen forces captures your imagination the most? Does the chilling possibility of vacuum decay unsettle you, or does the elegant mystery of quantum entanglement fill you with wonder? Share your thoughts in the comments below. Let's continue this exploration together. Thank you for joining us on this voyage into the unknown. Keep looking up at the night sky with that sense of awe and never stop asking the big questions. The universe is whispering its secrets, and the greatest discoveries are always still to come.